fact, whoop, hang on. Let me do chat, yeah, and then turn this off. Hi, all. You probably can't see me yet. I'm just checking stuff out here, making sure things work the way I want them to. Oh my goodness, you can't see anything there. That's ugly, but hi. Hi, everyone. Hopefully you can hear me, you can see me. Your chat is like a total mess right now, probably because I've got to find a better screen for it. There we go. Hopefully everyone hears me fine. I'm 5x9 or 5x5, however you want to say it. And yep, wonderful. Nick, you tell me I'm 5x9. Excellent. Lovely to see all of you. We have a very fun day planned here. For those of you on Patreon who have wondered, where have I been this week? You're about to find out. I've been desperately working super hard behind the scenes to code up some new data products. I've been working on this for like a year, and actually more than that, but really intensely for about a year, and finally have gotten things into a situation where they had, like over this last month, where we were really close. And so, you know, obviously being a sole person here behind the scenes as well as in front of the camera, everything is dictated by, you know, when can I fit something in? Can I do forecasting, or can I teach, or can I, you know, teach at Millersville, or can I create data products? It's all little bit by little bit, or, you know, go to conferences, that kind of thing. As many of you know, I don't do YouTube full time, right? I do it as much as I can, but it means sometimes I can't do forecasts if I've got something that's really important to do. And so that's where I've been, and I'm going to reveal some of that today for you. So get ready, buckle up, because it's going to be a bit fun, and you'll see very soon that for those who are behind the scenes with me, you get to help. Okay, we'll bring that out, and that's something, and you'll see some of the work that patrons as well as myself, what we've already accomplished, and it's just the tip of the iceberg. Things are going to get so cool, I think, here very, very quickly. So good. I'm so glad that you guys can see me and you can hear me. And what we are going to continue to do today, right? Let me go back to the title page here. Is and I'm going to try to get a mouse working, so that a remote mouse working, so that I don't have to walk away from the camera so much. I can just click, but it's not charged, sadly. So what we're doing today is the third in our data products for space weather forecasting series of courses. I thought I was going to get done today, but my goodness, it doesn't look like it. It depends. I think it's going to depend upon what the mini course tier of patrons really want me to do. If you guys want me to do deep dive in another kind of data product, which we'll go into a little bit today. Speaking of, let me just, I'll introduce these folks first. These are my mini course patrons. If it weren't for you all, I wouldn't be able to do what I do. And if you've just recently joined, you may not see your name up here yet. But it will be there the next time, I promise. It's just I haven't been able to update this since my last mini course. And that's because, as you'll see very soon, Are we better? Everybody better? These were brand new batteries, guys. I have no idea why they went out. So now it looks like I'm blasting. Yeah, the other batteries, they were just dead from the, like dead on arrival. So let me turn this down. It looks like it's slightly blasting out too much now. All right, hopefully that's a little bit better. Check, check. Okay. Can everybody hear me now? Okay. Ah, goodness, you know, technology. All right, so I'm not sure where I lost everyone, but thank you for my VIPs. They gave me a call so they know, and that's exactly who I was talking about. My VIP family, you know, we're all very close, and I don't really, because I'm so community driven, I don't really go anywhere or do anything without talking to them first, making sure that that's the right thing for the community. All of these folks have a vested interest and a toe in the water of space weather, and they've got so many different types of expertise, from people who are very scientifically driven, amateur radio operators, aurora photographers, and just space weather enthusiasts, and even heliobiology. So those who are curious what we're going to do with heliobiology, we are very active in that arena as well. And it's becoming a bigger and bigger deal. So if you are interested, please feel free to talk with any of these folks. You'll see that both Mike Richardson and Jerry Ryan are the moderators in the chat, and they are VIPs. You will also see a lot of other names here that are in the chat with you. So feel free to chat with those folks because they're very friendly, and they are wonderful people. Okay, so with that in mind, by the way, Patreon, all Patreon folks, if you guys want to just leave questions in the Patreon post for this particular mini course, I will take a look at them before we adjourn. You know, when we take breaks, I'll take a look to make sure you guys get your questions answered. Otherwise, feel free to join the chat here on YouTube, and I will do my best. Be nice to Mike and Jerry, because they will boot you if you get too far off topic. We'd rather keep the questions reasonably on topic, especially while I'm going through the charts. And then as we get to the end, or I get to big stopping points, that's when we can deviate and do some other fun talking about stuff. Okay, but they're good guys, so be nice to them. And if you ask questions and I'm not seeing them, highlight your question to Mike or Jerry and say, hey, you know, I've tried to put this question in the chat like 5 times and Tamitha still hasn't seen it. They will highlight it, because when their names come up, I see them very, very quickly, and my eyes go straight to them. Okay, so they can help you get, you know, raise your visibility if need be. All right. So we're going to have some fun today, because this, after the review, this is going to be a bit more like a laboratory. I'm going to go in and do some like live looking on YouTube, and not YouTube, but on the internet. As long as my technology behaves itself and actually loads pages, we'll see. Sometimes that's a pain. But I have 2 systems up today, so hopefully that will make a difference. These are the data products, or basically the regimes that we have covered thus far in Class 1 and Class 2. This is the D set of courses. So be aware that this is now D3, the 3rd one in the series. The first one, we went through most of this stuff into about inside the near-Earth system. I think at the D2 we had to cover more of these, which are the second set of data products. These are basically, in this regime, we've just covered the basics. We've not covered, you know, a deep dive in all these different data products, because they're all over the place, as you'll begin to see as we go into this next set. Okay, we're going to dig deeper into all of these arenas above, right? We're going to talk about additional as well as advanced products with similar functionalities to the ones that you saw with the basics. Some of them are just be like kind of the same thing, except maybe they've got a few more whistles and bells on them that make them a little bit more challenging to understand, but also that much more useful once you do understand them, right? And then we'll talk about web data product repositories, including NASA, ESA, and a few others like Kyoto, and which I've mentioned before, and the Australian Meteorological Bureau. How far we'll get into that, I don't really know, because this area could really just, I mean, it could have its own course in of itself. And then if we have time, I don't know if we're going to get to this, the public software and analysis tools. The reason for that is because these, again, also are tools that can be extremely challenging to use, and there's lots of features, And some of it, we'll see. But I doubt we'll get to this today. And then I'll just need to chat with my mini course folks, to find out where you guys want me to go from here. If you want me to dive into things like Helio Viewer, for example, or some of the other tools that can be used from a scientific perspective. All right. However, one of the first things I want to show you, okay, are some of the new data products that I've been working on. A lot of you know I am very much into working on the geochron. The reason why I think the geochron is so unbelievably powerful is because it is a data aggregator. I mean, it's a timepiece. It's meant to be a clock. That's how it started out. But once they got Patrick Bolin created a digital version of this clock, it became a data aggregating product. So as you can see, these are just 3 stale pictures at the moment, but I'll show you movies. This is, as you might recognize from our first mini course, right, the DRAP model. Well, here's an overlay of DRAP on the actual geochron. The geochron is a map of the world, but instead of just being a stale map, right, with just outlines of the countries, you can actually get all sorts of information on it, including live cloud layers. You can get precipitation, you can get airline flights, you can get the number of COVID cases, how many active earthquakes are going on through the fault lines, volcanoes, all sorts of things that you can get on the geochron as data layers. I am the one who's creating the space weather bundle for the geochron. I'm the official creator for it. So I'm super thrilled to be able to work with this group of folks. They're wonderful, and their data aggregation is, timepiece is second to none. It doesn't update every 5 or 10 minutes or even every 1 minute. It updates every second. So it is a timepiece. So it is meant to be a clock as well as a data aggregation unit. And it updates these overlying layers on a flat map, a Mercator projection of a flat map, as often as the data becomes available. Okay. So we've got the DRAP, which is for solar flares. If you guys remember the D1 class, we talked about DRAP, and we'll go over that in a review here shortly. I have the Ovation model, which you can see here, right? This is just, and these are really brand new, so I've got a lot of tweaking and things to do. And the latest data product that no one has seen yet, not even my VIPs, is ROTI. ROTI is the rate, essentially the rate of change of the total electron content. It's really how the total electron content as it's being measured is changing very quickly. We get a kind of what we call a standard deviation, which is kind of a measure of its error, and how quickly that is changing and how large that error is goes into the ROTI. What it is a kind of a proxy for the risk for scintillation. And if those of you who remember what scintillation is twinkle, twinkle, little star, right? It's the same kind of thing that you see with your eyes when you look at city lights in the distance, right? If you're sitting on a mountaintop and you're looking down and the lights are twinkling, how pretty, or you're looking up in the night sky and the stars twinkle, right? It's the whole reason why that song was sung to begin with. It's all basically the product of scintillation. Well, visible light scintillates, but so does radio waves. So radio, and so does GPS, because that's radio. It's all electromagnetic light. So the same stuff that you see happening that makes the lights beautiful in the night sky, that doesn't make radio waves so beautiful. It makes them hard to understand, or oftentimes just destroys them altogether. And so radio communications of all different types can get interfered with, let's say, degraded, interfered with, completely cut out, masked, all these types of things due to scintillation. And so to be able to have some kind of map that's showing where potential for active scintillation is high, along with some of these other space weather layers, is a real powerful asset, especially when you start using them together. So I can show you these data products, and I think what I'll do is I will show these after I do a review, okay? Because I have them on my other system. I'll pull up well, no, you know what? I'll show them now. Anybody want to see them now? I'm sure my VIPs are like, yes, please, please. So, because they know I've been working on this stuff. So let me see here if I don't know if I can get this thing working. so I don't have to go up. Does it work? Let me turn it on. If I don't have to go up to the, no, it's not charged enough yet. Poop. Oh well. Oh, that's too bad. It's still charging. I was hoping I could get it. All right, so hold on a second while I flip this over to the other system. Okay, so now we can hopefully see this. And see, I do have some live pages up here as well, because I plan to use them. Yes, okay. So let's see. We have, let's do DRAP first, and hopefully this will play without much of a hitch. Come on, off. Okay. So this is the DRAP layer on the geochron. As you can see, there are active geochron times right here, right, and it is moving. I have data. This is the night side of Earth. This is the day side of Earth, obviously. And these are ham radio contacts being done all over the world. You can also see active cloud formations, and if you look really closely, you might see green, because that layers, I have a very dim layer on that shows where the precipitation is, so where the rain is. And with the active, obviously with solar flares, when you're looking at DRAP, you're looking for things that are going to flare out, right? You're going to look for basically ionization in the D layer of the ionosphere. And when you have big solar flares, you're going to see that. It will change this from blue to red. Now, I have it very dim right now because I can adjust. As you can see, this is all layered in a Mercator projection. This is all done with Python. So I have active control over how these layers are being projected. And so I'm overlaying my DRAP, this layer, where there's a big flare right there. This was the flare we had on about 10 UTC on the 6th. That was almost an X-class flare. It was like an M, I can't remember, M something. And as a matter of fact, I could probably put the class of the flare up in here somewhere. But these are the types of things, and you can see the sun right here. So you see where we're going to have a big solar flares, where obviously where the sun is. So you get this nice kind of thing where you can see the analemma, right, where the sun actually goes in its figure 8. You can see what the amateur radio operators are doing at whatever frequency. You know, you can't read the frequencies right here. But once I get this integrated into Geochron, you're going to be able to see all of this and adjust all of this the way you'd like. However, until that time, I plan to have a certain cadence of these up on a website that active patrons can get. And the reason for that is because this is the development phase, right? That's why you see all this extra kind of scientific, plotting of stuff. I am actively going to be soliciting from behind the scenes patrons how to adjust this stuff. Do you like the masking? Do you like the color scheme? Do you like how overlaid it is? Do you want a different shape and a different color? Because I have different ways of plotting it over and over. All sorts of different choices. And these will be active conversations that we will have. Okay? So for those who are patron members, who are behind the scenes members, this is what we're going to do. And we're going to get together behind the scenes you can talk to me via like text or whatever. You can talk to me via we have chat rooms, and I will also come on Whereby, and we can actually have official Geochron, powwows, discussion, data product discussion sections that go on about this. So that's DRAP, right? And you've already seen it. You'll see another version of it. You'll see SWPC's version of it shortly, but that's my version. Okay, now here is Ovation. This is for, this is the data product for Aurora. Now, sadly, of course, Aurora hasn't been very exciting. We've had 2 solar storms, including one today that's hitting, that they're all northward fields. So the Aurora's been terrible. So this isn't a real good test of the Aurora, but you can see it here. Again, this will look slightly different than the projections that you see at SWPC or anywhere else, because they don't use Mercator projections. Mercator projections, if you're familiar with the type of cartography I'm talking about, Mercator projections really stretch out the higher latitudes. Okay? That's why Greenland looks so big. But what's neat about that is that it really begins to expand this area and give you a better idea as to where the Aurora is going to be happening at high latitudes, right? Where the other maps squish that area so badly that to me, they're almost useless for Aurora photographers who might want to look at it. And who don't use some of the other tools and more specific tools that are available to them. But with a Mercator projection, it's actually designed perfectly for this kind of thing. Now, if we only had a big storm, right, that can actually give us a lot more than this. This is, as you can see, is extremely sensitive. I have only a 3 gigawatt threshold. SWPC right now uses a 5 gigawatt threshold. That's why you can see the aurora extent even at a very, very, very low modeling threshold. This is, once again, something that we will discuss. Do we like the colors? Do we like the scheme of things? Do we like the opacity? Right? And it doesn't even have to, soon I won't have to have ham radio lines on here. I just have them here because I just have a single base map as I test this stuff out. So understand that there's a lot yet to do when it comes to this. And I would love to hear people's, behind the scenes, I'd love to hear people's impression and their, you know, their desirements. Give me some desirements, right? Not requirements, but desirements. Okay. Now this one, this is the newest. This is ROTI, okay? This is that scintillation index, sort of. It's not really scintillation. If you called it a scintillation index, you're going to get your hand slapped by scientists because it's not really true. It shows the risk for scintillation. And today we will go into the data product at the DLR that actually creates the data that I'm using here. Okay, so this is not SWPC data. And yeah, every now and again you'll see a shift because you'll see this shifting. And the reason why this line here is shifting is because how the Mercator projecting, basically the range of the data overlay. And it shifts how it works. So ignore that. Don't worry. Everything's still working fine. But it may make the map shift a little bit here and there. I just haven't locked it down yet. Okay? But what you're looking at, and I've got it really, really dim, right? But you'll see, every now and again, you'll see these little red splotches. Now, the big splotches are probably not as real as, and not nearly as extended as the littler splotches. When you see little splotches, those are probably very intense and high risk for scintillation. This is a very, what we call a sparse data set, okay? We only have data in and around land masses because that's where we have GPS receivers. What's actually happening is that you actually have GPS satellites flying overhead, and you've got a receiver that's checking how that signal, what that signal looks like, essentially, as that GPS satellite flies overhead. So you get these, what we call pierce points, that actually move across the sky as the GPS satellites move. Okay, and you can calculate how ratty looking that signal is, essentially, and that factors into how you do ROTI. Now, because you can't cover the entire sky this way, right, it means that the data set is sparse and some of the data lines will be really stretched out. So when you see huge swaths of red, let's say, or even green, likely that's not as robust an indicator, right? It's probably not scintillation or risk for scintillation in that whole area, but at least it gives you some idea of, okay, in this region, there are potential issues, okay? And what I've noticed already, just by looking at this, is that I can tell scintillation happens not only far much more in the evening, right? And far much more, which we already knew, and far much more in something what we call the equatorial anomaly, which we will get. That's another data product. That's the total electron content, which will reveal these two bands that come across this way near the equatorial region. But what I'm also noticing already, because we have the cloud overlay, I'm already noticing that scintillation has a tendency to happen for this ROTI index peaks. The risk for scintillation has a tendency to be far more clustered over either active storm centers or high movement, like storm fronts. I'm already noticing that just as a casual observer looking at one day. So having this data aggregation where you have cloud layers and terrestrial weather along with what is space weather, having these products together really opens a whole new world of observation and analysis for all of us. And I am absolutely thrilled, even though that this is, you have to interpret this data very carefully. Yeah, look at these big plotches. Those aren't real, okay? You might have one tiny little spot that has a scintillation, but you have no other data points up there, so the computer just kind of spreads it out. And for me, that's fine. I'd rather have that than the way we look at it, which I'll show you soon, is another way of looking at it. I actually prefer this method just because it's easier, it's softer on the eyes, and I can see a bit more of what the potential for scintillation might be, right? But these are things again that we will be talking on, and that you can see I've run out of scintillation maps. I think this movie's almost over. These things will be things that we will be talking about behind the scenes, and we'll be able to make a lot more adjustments of how we view it. Again, what the color range is, what the opacity is. You see numbers going crazy up here. I'm still doing it. As you can see, I'm still in the debugging phase. So you can see max and min ROTI up here. I can display all sorts of stuff. Okay, so these are things I want help with, right? And then what data products do we do next, right? WAM IPE is a low-hanging fruit, but there are others. TEC, for example. Actually, I'll get that from WAM IPE. There are others that we can exploit and map, and it's going to become easier and easier the more maps I make. So, yeah, as I go back to this slide here, as you'll see, our community on Patreon, right, is helping to create and shape these new data product visualizations. So join us there if you want a voice, right? And behind the scenes patrons, you will get here very quickly. I will be posting something where you will get access to a whole special little chat room and a special little place where we can all get together and talk about it, okay? I think it's going to be a lot of fun. All right, hopefully this stuff is cool. Hopefully you guys like this. Give me thumbs up or thumbs down, or I don't know what the heck you just showed me. It looked bizarre. All of that works, okay? And before we dive into some of the new stuff, like you know, these big data repositories, let's do a quick review, okay? And just like I showed in the prior with the prior movies, think of space weather data products in aggregate, right? Because when you take some of these data products and you do it alone, they provide a certain amount of information, sure. But if you can look at them together, you find the ones that really work together, then that will tell you so much more about space weather. Because if there's anything I have, cool, I'm seeing everybody with a thumbs up now, thank you. Because if there's something I have learned in my, you know, unbelievably, sadly, long career in space weather, I'm getting old. If there's anything I've learned from all of this, it's that space weather, any one phenomena only perturbs the system a little bit, right? Unless, of course, we're sitting at a G5, then, you know, all bets are off. But if we're sitting at just a regular storm, there are inconveniences. It's like weather. It's like a drizzle or a slight rainstorm or something, right? The rainstorm, for example, with terrestrial weather, the rainstorm becomes a problem if it hasn't rained for a while, because when it rains, then the roads get slick because there's a lot of oil on the road. So it's not just the rainstorm, a light drizzle, that causes the problem. It's the light drizzle combined with the oily roads that make for big disasters, right? So that's kind of what space weather is like typically. It's like small drizzles. But if those small drizzles aren't acting alone, if there are more than one space weather outage, or that space weather problem is coupled with the terrestrial weather problem, now you got big problems. Now you got the potential for real impacts. And so that's kind of the way, as I'm building these new data products, it's kind of the way I like to look at it, right? Is that you want to be able to layer all this stuff on top of each other, so you're aware of all of these different things at once, so that you can really understand and ascertain the risk, okay, of what you're dealing with. So keep all that in mind as we do this review, okay? Think about the data products that can be used together to help inform your you know, where you are, what you're doing, especially if you're an emergency responder, a satellite operator, that type of thing, okay? So I'm going to just go through a lot of the slides that I went through before. Okay. Yeah, just checking. Good. I'm so glad people like stuff. Okay. I'm going to show a lot of the slides that I did before, right? But we're going to go through them quickly. Okay. So Space Weather Prediction Center, right? It's the reliable source of space weather impacts for the Northern Hemisphere, right? We went through a lot of this stuff. I kind of walked you through what was going on the front page, on the front page of the site. We went through all of these data products. If I recall, I think we even went through this one. Radiation storms, I believe we did. I'm picking out some highlights, right? So if any of this seems alien or unknown to you, just take a look at Class D1, okay, the first one in the series that we're in. Space Weather Prediction Center's data products, whether they're observationally based or model based, or what they call experimental, which is where they shove everything else. It's not experimental. ACE is not experimental. ACE is a veteran. I always feel badly that ACE is put under here. It's like, that's not experimental. This thing's older than Discover. So, but all of their stuff is here, okay? And you can even get alerts, watches, and warnings. I am not going over this in any detail. If you guys really want me to, where I do a deep dive of this repository and go through everything, I can, right? A lot of it you'll probably sit there and yawn about, because here they're trying to cover every stakeholder there is, right? And so, and on top of that, some of their data products, of course, are geared toward government agencies and government systems that have been in place for decades. And so their data products may look a little tired because they have to keep them that way, especially when you look at some of the forecast reports, you know, or the forecasts here, and you see some of their text products. It's like, why is it formatted like this? This is silly. Well, it's because the system on the other end that ingests those reports constantly will break if you change it. Okay, so that's part of the reason why this is so calcified. Okay, trust me, a lot of these folks that work here don't want it to be that way. It just, you know, that's just the name of the game. When you work with the government, you're not there just for yourself. You have to serve lots of different stakeholders. So that's why that is like that. So let's talk a little bit. Let's kind of go regime by regime. Okay, so we're going to talk first about solar imagery, on-disk analysis, and coronagraphs. I'm going to do it quickly. Right. Here was SUVI. Do you guys remember SUVI? Okay, you just look it up. It's one of the data products. You have all sorts of different colors, right? Here's a solar minimum sun, in case you forgot what it looked like. But you have all these different colors, including the red sun that you can't see. Red is good for material coming off of the sun. If you want more information about the phenomena, what you're looking for in these types of images, you need to look back at the C-Course series, which is all about coronagraph or CMEs. And then I go into solar flares. You can look at, I think it's the F-Course series, which is all about solar flares and radio bursts. And that gives you a lot of insight into what the phenomenology is and why you would look at one particular color sun over another. Here you would just click on any of these and up comes the image. And then down at the bottom of this, you can't see it's kind of cut off here, but down at the bottom of this is that bar, that progress bar that will show you the movie over the last 2 hours or so. Again, I covered all of this in the first class. Another one that does something very similar is if you go to SDO. Remember SDO? This is a scientific grade instrument, so the resolution is a bit better. Its cadence is lower, so meaning it doesn't give you as many images as fast. And it doesn't extend out way out into the middle corona like SUVI does. So if you want to see something off of the limb of the sun and out further into the middle corona, where you go is SUVI. If you want to see higher detail and resolution in the actual disk of the sun, you go to SDO AIA. Okay? And again, we talked a lot about this in the first. And yes, this is a different site, right? This is Goddard. And I believe, hopefully I put that link in the first set of charts. I don't know. But it's easy to find. SDO .nasa.gov, something like that. Oh, sdo.gsfc.nasa.gov, probably. Anyway, then if we go out to coronagraphs, right? So now we're eclipsing the sun on purpose because the sun is too bright. And so by putting an occulting disk, now you can see the corona and you can see stars. Oh, wow, look, stars. People go, well, obviously the disk is CGI, right? SUVI and AIA are CGI because you can't see stars. No, it's because if you wanted to image the stars, you would have to open up the aperture so much that the sun would blind you and probably damage your instrument. So they stop it down, and now you can't see the stars because the stars aren't bright enough to compete with the sun, right? Because it's a big star ourselves. So here, if you blot out the star with an occulting disk and just put the outline where the star is, right here or here in the C2 field of view or the C3 field of view, suddenly you can see stars and cosmic ray streaks and all sorts of fun little things and planets, right? Not aliens, planets. And then you can get all sorts of artifacts as well. This is an occulting disk arm. This is the thing that holds the occulting disk. We call the pylon, right? And of course the sun is different sizes. The occulting disk is a different size depending upon which field of view you're looking at. This one goes out to 6 Earth radii, or Earth, 6 solar radii. This goes out to, what, 15? No, 30 solar radii. And what you see in them are chronographs, or coronal mass ejections, right? Because it's scattered white light, and it gives us an idea. It's still the main tool we use to determine what we're, what the direction, what the speed, whether something's headed toward Earth, how soon is it going to get here. It informs models for us. Okay. I left in, this is seeds. This is how you get to, right, this is the solar eruptive event detection system. This is an automated system. There's also cactus. I went over those last time, and you can see how it automates finding fronts of different events. Here's a nice coronagraph. You can see here a difference image as opposed to the raw imagery. Sometimes halos are extremely light and you can't really see them in the raw imagery. So you use difference images to enhance those features. Right, and you can see the disk, you can see a front, you can sometimes see multiple different events leaping off. So there's one, and then you can see here is a halo. Whereas in the raw imagery, you may not see that. Look, raw imagery looks terrible. Plus, in the raw imagery, you see the planets quite well, which disappear essentially when you do difference imagery because they're not really moving. So they stay the same. Of course, synoptic charts are important, right? We talked about those, and if you go to, is this going to keep playing? Oh, I wish it would loop. Oh well. If you go to the Space Weather Prediction Center, you can find these done every day, and they give you all sorts of information about the flaring capability or whatever of over the total disk, and then each different sunspot grouping will have its own that mimics this. Remember I talked about this, and I talked about who the forecaster is, what time they did it, what's the next active region that they're going to pop up, what Carrington rotation that is, meaning because we log all this stuff, meaning what part of the disk are we looking at. And then there's all sorts of times and images that they looked, or times of the imagery that they looked at to draw all of these features. And some of the features are drawn using like Photoshop tools, and some of them are hand-drawn. Most of them are hand-drawn at this point, but I'm now seeing several. Terry Spencer has managed to get a few people at SWPC to start drawing with digital tools, which is kind of cool. It's fun seeing the evolution of things as they go on. HMI, of course, observations are incredibly powerful because they can show details, magnetic details of an active region, and you can see the magnetic field going out or into the plane of the page, meaning with, in this case, blue and red. You don't want blue to touch red, right? Just like what I said with American politics. If blue and red gets in the same room, there's fireworks, right? So anytime these regions, you start seeing a lot of magnetic mixing of the different colors, that ups the flare potential. And it gives you a lot more information than just looking at white light diagrams, right? On top of that, some won't even be sunspots. See, it'd be just a plage, like a little light region. And yet, on HMI, boy, it's still big. Okay? So it gives you a lot more information about these regions as they rotate in and out of view, and also, which also gives you more information about, like, let's say how bright, how much solar flux you might be getting. Because this may not look like all that much, but if you see it in HMI, you're like, oh, okay, this is emitting a lot of light. And sure enough, you can really, if you really look, you go, oh, there's the plage. Okay, I see. So you can kind of wonder, why am I getting so much, why is the solar flux so high when there aren't really any sunspots on the disk? Well, just take a look at HMI and see if you see more activity. Of course, X-ray flux is a big one. This was once again done during solar minimum. You can tell because the X-ray floor is so low, right? It's sitting just below the B floor. We don't have that now. Here we're between the C and M floor. It's like a C3, C4, I think is our floor right now. And that's because we just have so much more activity going on. Even just the base sun is a lot brighter because we're just outside of solar maximum. But we like X-ray flux because it gives us such a huge dynamic range, right? You can go 7 or 9 orders of magnitude depending upon what you're looking at. And of course, we take a look at the top, which is the long wavelengths, the lower energy X-ray flux. That's how we measure whether we have a A class, B class, C class, M class, or X class flare. Typically, we don't care about A and B. We hardly care about Bs. We might care about them a little bit when we're at solar minimum because we're bored, but we don't. It doesn't really mean anything. Around a C class flare, amateur radio operators go, what was that? And then an M class flare, they go, oh, God, is my rig? What's wrong with my rig? That's where you start having problems where you get your first radio blackout at an R1 level. M5 is an R2 level. An X1 is an R3 level, and then you go up. You don't typically get really high flares. An R4 to an R5 level radio blackout are much more rare than a 1, 2, or 3. In fact, I don't even bother forecasting 4s or 5s because they're rare enough that if you're going to get an R3 level radio blackout, if you're an amateur radio operator, you're not communicating to anybody. It's all over. So anything above it is like, okay, maybe it'll last longer, All right. So, and yeah, for this, please remember, please, CMX class flares are not CMEs. Don't say we have an X class CME. Don't say it. Oh, we have an X class event coming toward us and it's going to give us a big storm. That's not true. That's not true. These classes are for flares only. Okay? There have been many X class flares that don't even launch. There's not even a CME that's launched with these things. Flares and CMEs are two totally different phenomena. They don't have to happen together. In fact, we can get a very strong CME launched with no flare signature at all. They're called filament eruptions. Okay? So, there have been many times where we've gotten G3 level storms. But if you go to the X-ray flux indicator to look for the flare that was associated with it, you won't find one. You might find maybe a very slow burning C-class flare, maybe, but you won't even recognize it as such because it's so low level. So do not conflate solar flares with coronal mass ejections. Just don't, because you will be forever confused, okay? Because they don't match at all. All right. Interplanetary space. Now let's talk about NLL, right? You guys see me use this thing all the time, right? Top panels density, bottom panels velocity, right? You say it all the time in the forecast anytime there's a storm coming. We will look today at several other versions of NLL or these solar storm prediction models. NLL is just essentially the first. I remember when Dushan was creating it. I remember him. I remember when he was posting it back in, what was it, Solar Wind 9. And he was doing a talk on it. I'm like, this is really cool. Can you do flux ropes? And he's like, no, not yet. So I remember when this thing was just starting. I was a grad student at the time. And I was just thrilled to see this thing because it was the first time we ever had a model that actually kind of gave us like an actual, trek through from the sun to Earth in solar wind, in actual solar wind. And it's come a long way since then. It's a bit ubiquitous. But our community will always be grateful to Dushan Odstrasil for this model because of how much it has been used. And again, I'm not going to go through the details, but we've run it in the last class, or in D1, I think we ran it, and you know, you have these little bubbles of stuff that come out. Now, these little bubbles of stuff, these little plasma blobs that come out, are not, they're not as realistic as we'd like them to be. And the reason for that is that if we were to make them as realistic as we'd like them to be, well, then we would never get this model done before the CME itself hit us, or the ICME hit us. Excuse me while I wipe my nose here, itchy. Okay. So we end up having to run something that really just has magnetic field in it as a tracer. It doesn't exert any forces, and so you'll see CMEs that smash into each other and cannibalize each other. That doesn't happen in real life. Coronal mass ejections will pancake and be really smashed up and kind of cross into each other just a little bit, like, you know, the front end of that will kind of smash into the back of that, but it won't go very far. It's not gonna, you're not gonna, even in some of the ones, and I think the one that I gave an example of was the May 10th storm. We had like 8 different CMEs. I mean, there was just so many, bang, 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 all at once. And the last one was like the fastest, and it caught up with all of them. And in the Enlil model, they all kind of just merged together. Whereas if you actually look at the solar wind from that day, you see you see areas, different regions where things go up and down, and you actually can tell, okay, here's where one probably stops and the next one starts, and then that one stops and this one starts, and oh, this one looks like it bled into this one a little bit, but you can actually see these discontinuities in the solar wind where these structures got smooshed together, but they didn't just blend together like paint. It doesn't work like that. And the reason for that in real life is because of the magnetic field. Again, the magnetic field in here, just along for the ride. So it's not exerting the forces that it does in real life, okay? So there are limitations to these models. But overall, Enlil does a pretty good job of predicting the arrival time, okay? And we'll talk more about some of these others later today. Oh, I did keep it in. I thought I didn't keep it in. So here's that example, right, where you've got so many events coming out. Boom, 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 boom. And they just all merge together into a single mess. That is this is not what it looks like in the solar wind. Okay, so when we actually look at the real solar wind, it's not like that. It's interesting. It looks in the solar wind, the magnetic field looks kind of more like this, where you can kind of still see, at least in the velocity regime, you can actually still see the separate indicators. Here the magnetic, like I said, the magnetic field just kind of all just smashes together. So just be aware of the pluses and the negatives of Enlil, and use it wisely. Okay. All right. Real-time solar wind. Of course, this is the tool of geomagnetic forecasters when they're trying to get an idea of what a storm is going to do when it hits Earth, right? And lately, the magnetic field has been, sadly, of all the storms, have been pretty much northward. We need southward magnetic field, so in other words, this red line needs to be less than 0, and it isn't always like that, right? Last time I went through this in great detail. I'm not going to take the time to do it today, but just remember that it's really the southward component of the magnetic field that matters the most. After that, probably BY. And I don't know if I talked too much about that, but that's an advanced topic where the BY component of the field actually does play a role in creating stronger currents that then can drive substorms as well as stronger aurora. And for spacecraft operators, especially in Leo, in Mio and Leo, it can also drive bigger bursty bulk flows that get shot down into the polar regions and can charge spacecraft up pretty tremendously. So you have to be aware of BY as well as BZ. But yeah, that's, our upstream monitor that gives us anywhere between, if it's super fast storm, only gives us maybe 15 to 20 minutes heads up. If it's a super slow storm, it can give us up to about an hour heads up of what is coming, right? It all depends upon the speed of the solar wind coming at us, because the upstream monitor sits around 400 and some odd Earth radii ahead of Earth, sunward of Earth. Okay. All right, so let's go inside the near Earth system. right? And I showed you the model magnetosphere. Okay, this is it's not data. You out of here? Okay, bye, babe. I'll see you soon. This is not data, and I can't tell you how many people have gone on and looked at this and thought that this was data. And again, I've gone over this before, right? This is still just a review. You're looking at, in this case, you're looking at velocity. This is Vx, so you're looking at velocity, or speed rather, either speed in this direction or speed in this direction, okay? Speed, cute. Huh. It just dawned on me. This is geographically wrong. Can I move this up? I think I have a next slide. Oh, they did that wrong. How funny. The problem that we have, and I'll leave it here because I'm going to do a movie in a sec. The problem that we have with this, and it just dawned on me, I don't think I talked about this last time because I didn't think I actually caught it, is the GSE coordinate or GSM coordinates that I'm sure this is in. Right? Do you have it labeled? No, of course you don't. This is in GSM coordinates, guaranteed. And so you have, it's labeled X and Y, but they're not saying what coordinate system it's in. So that's centered on the Earth, okay, with the positive X direction being toward the sun, okay? See how this is wrong? They have positive X direction going this way, right? I can't point that way, right? Positive X is actually going this way, okay? Actually, they're having it, yeah, you can see it down here. Positive X going this way. So Vx was, when they put these little arrows here, they should have done it the other way, right? They should have flipped this bar over because it makes people think, if they're not paying attention to the numbers very, very carefully, it makes people think that this direction is going to be, if you have solar wind moving this, moving this direction, it's going to be red, and if solar wind is moving this direction, or wind rather, let me just say speed of the plasma is moving this direction, it's going to be blue, and that's not the way it is, okay? And that's why I paused on that other one, because it was like, wait a minute, why is red pointing this direction? Solar wind's coming in this way, okay? In a minus direction. In GSM coordinates, solar wind blows this way, right? That's why it's all red, because it's negative. Typically minus 400 kilometers a second, maybe a little bit faster, okay? Depending upon if you're in a fast wind stream or not. Okay. So it blows this way. That's why you have a bow shock here in front of it. Okay. And we are looking down at the Earth from the North Pole here in this one. In this version, the North Pole, you're looking down this way. That's the North Pole up there. That's the South Pole there, because you're in the Z coordinate. Okay. Nonetheless, the solar wind is still blowing in this way. Okay. Negative, right? Where you get positive solar or positive wind, I got to be careful. It's not solar wind. It's now positive moving plasma, because now you're in the Earth's magnetic system in here. This isn't solar wind anymore. Okay. Where you get the positive stuff is blowing this way. Why? And I shouldn't say blowing, I should say slingshotting, because this is the Earth's magnetic field, the tail of the Earth's magnetic system, and when you mass load it and you pull it back, you're loading the slingshot, and then it goes boink like this, and it fires everything forward. And as it fires stuff forward, you see blue. You can even see it here, blue going up and into the poles, okay? But it looks like the arrow would point that way. No. They've got this thing backwards. They should have just mislabeled, because it's still labeled positive. See that? But you have to look down here to realize positive is actually this direction. See the positive 0? Or positive 0. Positive in front of 0 going bigger this way? Yeah. So the positive direction is that way. The negative direction is this way. Okay? This is very confusing. And it kills me that I didn't notice that last time. So be aware of that on SWPC. Boy, that's painful to try to teach. Take this bar and just flip it, okay? The numbers can stay the same, right? Because red is still negative, blue is still positive, but take the arrows and flip them over, please. Flip the thing over the other. Anyway, all right. So why I talked about this and why it's useful is that it can tell you how disturbed the magnetic system is. It can tell you where let's say, to a general degree, where the Earth's bow shock is, okay, and how far in it's come if you have a really strong, storm, and it can verify what you're seeing in magnetometer data at GOES. Okay, and we talked about magnetometer data. Those few of you who are really savvy aurora photographers know how to use magnetometer data to look for substorms. Okay, with a caveat. The caveat is that you better be in the Western Hemisphere, because if you're on the other side, if you're in Europe, well, you're going to have problems because these spacecraft are not hovering. These are geostationary spacecraft. They're not hovering over the tail on your side of Earth. They're going to be on the day side of Earth when you need them to be in the tail of Earth, because that's where the slingshot is, right? But they're on the day side, so they're not going to do a very good job of letting you know where substorms are. They'll let you know eventually, maybe, if you're lucky, but not very well. So you have to be aware of that. And that's why they put midnight, MMNN, noon, midnight. Why are there two? Because there's two traces, right? The red corresponds to the red trace, the blue corresponds to the blue trace. So you can see when the spacecraft are at midnight, and as they continue moving, as they orbit around Earth, right? Now they're rotating and orbiting toward noon. Now they're in noon, and then they orbit back toward midnight. And that's where you actually know, this is where the east and west coast of the United States are, right? East coast of the United States and the west coast of the United States, how they travel. Well, one of them passed midnight at this time, one of them passed midnight at this time. So here's when the United States is over noon. Here's when the United States is over midnight. Get me? So they're really US focused, or in this case, Western Hemisphere focused. Canada gets a freebie because the Space Weather Prediction Center is all focused on the United States. But every now and again, you'll get some weird thing like this, right? Where this thing jumps out and is like, ooh, is this real? Yeah, this is when we actually jumped out of the pristine magnetosphere. See, like my little spacecraft, remember I showed you this last time? The pristine magnetosphere into actually the magnetosheath. So imagine if you have a geosynchronous spacecraft right here, and when you get hit really hard by a storm, sometimes you'll actually pop out. See, here you're still in the pristine, ooh, look, okay? You're actually popping out. And I actually probably put that too far, because that's actually probably the bow shock. I probably should have put it in here, because this is probably the pristine region. So here you're actually in the magnetosheath. So I actually pushed that too far. You'd probably be more like here. Right? This is the boundary between, yeah, I pushed it too far. You're in the magnetosheath here. If outside, you're completely outside in the solar wind. That doesn't typically happen with storms, unless it's like a Carrington event. And then, yes, that kind of thing can happen. But, yeah, so I do have the little spacecraft pushed a little too far out. I'll be sure to move it in next time. But as you can see, here's the blue, right? And it does. It looks like a wishbone, doesn't it? Because you got plasma that's being slingshotted up, and it goes both the north and the south and goes into the poles. This is how we get aurora, right? So you can actually see that. But that doesn't mean the solar wind reversed. There's no solar wind in the Earth's magnetic system. This is the big skillet that spins stuff around and stirs it up quite dramatically. Okay? But this can help you if you're really looking at dynamics, especially when you've got a really big storm like this, like the May 5th one, the May 10th one, right? This is I happened to just capture a snippet of it in real time as it was happening. And it's just, look at the dynamics, pretty crazy during that. But that was kind of a fun exercise. So remember that, this indicator should have been reversed. And just recognize that in case you ever forget, right, you can see this bow shock, and it looks like stuff is blowing this way. So know that when it's red and it's blowing this way, okay, it's going to be negative. And that's the direction of the normal solar wind. All right. Yes, it did. So I went into radiation storms, and at the time I think we did this, we had a radiation storm. Oh no, this is a different time, September. I didn't do this. This was a recent one. Radiation storms are nice. There are multiple thresholds, right? Depends upon the energy. The red is the low energy stuff, relatively low, right? 10 MeV and above. And then the green shows 100 MeV and above. We have 2 indicators for an S1 threshold. The only one that SWPC shows labeled on their website is for the 10 MeV, this one here. If this gets above that line, you have an S1 radiation storm. And then you can go to an S2 if it gets above that line, and an S3 if it gets above that line. You can also have a radiation storm if this green line gets above this one down here. And I wish they really would put a 100 MeV threshold this way. The reason why they have that is because it doesn't take as much flux for 100 MeV particles to become a danger, because they can penetrate far more intensely through fuselages of aircraft, let's say. A lot of these particles don't do so well. These can penetrate much more deeply. And so you don't need as big a flux of them for them to be more dangerous. Now, that is also being said with a caveat, because it really depends upon what they're penetrating. Because if a particle, what really is the key is that whatever the particle is doing, how much ever energy it has, whatever it penetrates, if that material can stop the particle in the material itself, that's when you get the biggest deposit of energy. So sometimes that is actually lower energy stuff. So radiation is a real tricky bag, okay, when it comes to what are the most dangerous particles. Because they're hard to shield for. The more energetic ones are really hard to shield for, but the low energy stuff has really high fluxes and can damage really thin materials. So it depends upon if you're a human, or if you're a spacecraft, or you're an optical coating, or a paint, thermal coating, let's say. You can have all sorts of different energies causing different problems. Like thin paints and and thermal coatings, for example, they don't care. They don't care if you get 100 MeV. They prefer it. They don't like these. So it really depends upon what your application is as to what is the more dangerous radiation for you. And we talked a little bit about that, not too much. That's a whole nother ball of wax that we'd have to get into regarding like parts and thermal blankets and all sorts of spacecraft materials that would probably make everybody go, right? So we won't talk about that. Maybe we'll talk about it sometime with heliobiology. We'll talk more about how it affects organs and tissues for those who plan to go out, and become Mars colonists. You're going to need to know that stuff, I guarantee it. All right, solar cycle progression. There's multiple places to get it. We've talked about this before, right? We're still in the review. There are some places that actually are really great because they not just show projections and what's going on at the moment, but they will show other, like the Macintosh, right? And I'll talk about a site today that does that. SWPC has this essentially in their in one of their I think it's in forecast. And if you go to the data products and you look under forecast, they've got the solar cycle progression. They've got it for both sunspot number, and they also have it for F10.7. Sadly, you can see the consensus prediction is pretty far off. They continue to update that. The F10.7, do I have that here? Oh, I'm going to show that. Okay. F10.7 you can also get at, okay, so let me go back for a sec. Solar sunspot number obviously is not, because you'll see two things at SWPC space weather, the forecast prediction area. You'll see sunspot number, and then you'll see F10.7. Sunspot number and F10.7 aren't the same thing, right? Sunspot number is literally counting the sunspots on the sun. F10.7 is a particular flux at a particular frequency. I forget the frequency right off the top of my head, but it's a radio frequency, okay? And 10.7, 2,800 megahertz. I knew I wrote it down. So 10.7 centimeters. And you can get that data from multiple places, not just SWPC. You can also get it at Lizard, the Penticton radio flux. You can get it here, and you can get multiple, I I think multiple times a day, 3 times a day that they look at it. And I talked about that in more detail. And then I talked a little bit about how you use them together. So here's F10.7 at SWPC, and then the Penticton at Lizard is behind you. And then if you combined X-ray flux and at F10.7, you can get a better feel for what's going to be happening and how things are progressing. I talked a bit more. I think I probably even have this. Here's like an example of the noise floor rising and the noise floor falling. You can see that is going to give you potentially an indicator whether you're going to have big solar flares, whether the solar flux is going to rise quite dramatically. Whereas you may not get that with only 3 points a day if you're only looking at X-ray, F10.7, right? So even though this isn't necessarily the same thing as F10.7, it can give you an indicator whether or not the solar flux is going to rise or fall over a period of time of, of course, over the course of a day, right, where this may not. So it's useful, see? Okay. All right, DRAP, hey, there's one we recognize, right? So this is SWPC's version of DRAP. Okay, this is the ionization of the D layer of the ionosphere. It basically shows you where radio blackouts are going to be. Okay, in this case, we have a radio blackout from just a solar flare, and we have radio blackout from what we call a polar cap absorption event from a radiation storm. But as you can see, it smushes this, differing from my version of DRAP on the geochron. This is really smushing those polar regions quite a bit. So you can't see, if you're in these upper areas, you can't see very well. And of course, it doesn't have any terrestrial weather or anything like it. It's just very, very, it's meant for one thing. And it is a model. So you can see the day side, and then of course the night side is black, right? But this is one of the layers that I'm using, that I'm doing on the geochron already. And what I'm going to solicit help from with you guys. Maybe I'll help try to integrate some of this information into the version I have. We'll see. And you can see when the radiation storms pick up. I think this will show, is this, oh, this is from the 10th. Okay, so this is from the May 10th event. I'll play it for just a moment so that you can just watch it move. There's a couple big solar flares. And we might get a radiation storm from that, I'm not sure. Radiation storms do have a tendency to pop on. One of the nice things now, you don't get to see the analemma on this to know where the sun is, but you can kind of tell that you're in the northern hemisphere summer because you get all this glow, because this is the land of the midnight sun up here. So they see sun 24/7. So radio bursts and radio bursts and radio blackouts, ionization from the D layer of the ionosphere, can be a lot more problematic for people if they're really, really big flares, if they're up here, especially for aviators where the sun is oftentimes very much along the horizon and they're staring straight at it, or it's along the line of sight of their radio communications. It can be really problematic for them. I don't know if we're going to get a radiation storm. No, it doesn't look like it. So sorry, that's all just solar flare. But you saw with the polar cap absorption event when it comes really, really red hot, both in the north and the south. It's really easy to tell solar flares from radiation storms for that reason, even during the summer, okay? Because even during the summer, this fades. It's always like a bluish color, whereas radiation storms will typically be orange, yellow, orange, and red, okay? Because the polar cap absorption events are pretty intense, and they always affect really high, up to high frequencies in the HF range. Ovation. Right? The Ovation model, you've seen it probably many times. Ovation is wonderful for what it is as a model, right? But it doesn't capture a lot of the dynamics, and it doesn't necessarily capture, sometimes it can capture intensifications. But intensifications in real life, right? This is not necessarily this period of time, but you can see how dynamic the aurora actually is. These are from all sky cameras showing how dramatically different real aurora looks from this, right? And notice there was an artifact. I'm working to make sure that those artifacts are masked in my version. One of the things in geochron that we can do too is I can put a view line, but see this is an artifact that doesn't exist. Okay, they needed to have masked it out and they didn't. Ovation does have some artifacts in it. if you're working with the raw data. But they are useful. Okay. Now ground level. I wonder why I put that back up. KP. Right, we talked about KP. It's 3 hours averaged, right? It's used to be a stoplight chart, red, yellow, green, but now SWPC has made it be this kind of bar that anything below KP5, which is the storm level, okay, is green, which is sad because a lot of people can see aurora and you can get scintillation clear down at mid-latitudes from a KP4 storm. So I get frustrated that they lump all of this down in there. I preferred their old version where they would make at least a KP4 be yellow, but they've chosen this as their methodology. Obviously, G5 storms don't happen all that often, and they peg at KP of 9. We will look at, we looked at HP30, which I'll show in just a minute, that actually doesn't put a cap on it at 9 because the geomagnetic storm index should be able to go higher than that. There's no reason for us to cap it anymore, but it's historic. So that's what we did way back when, so we keep everything consistent. You can get station Ks, meaning same kind of process as for KP, but it's not planetary. You take the P away, and it's just for that local area where that station exists. And yeah, a lot of them label their things differently, as you can see. So can't necessarily trust the color to be the same and be consistent throughout. Here's what KP looks like in this nomenclature. It looks like this. For big storms here, it only goes to a dark red. Okay, so be aware of that. And I talked a little bit about AP and how AP takes a long period of KP and just locks it down into a small set. You get one AP, you take all this and you average it down, or add it all up rather, and that is one measurement. And then you get another, excuse me, this first day is this green bar, I missed it. The second day is this next one, and then so on and so on and so on. So AP is not very useful when it comes to radio propagation. It's better for climatology. Even KP isn't all that great for climatology, or for weather, for space weather, because it's giving you a 3-hour average, right? And we talk about why we, let me go, why we use HP, and I think I have that coming up soon. KP and AP, though, if you're going to use them, right, they're more for the night side, okay, for aurora, for radio propagation on the night side. X-ray flux in F10.7 is far more. We use it in conjunction with DRAP to get day-side disruptions of the ionosphere for radio propagation. Okay. So be aware that these different indices are used differently for different parts of Earth. And then, yes, I went into HP30 from GFC, right? So here's the planetary K here. And in this case, they only do a stoplight chart, green, yellow, red. Their yellow, I think, starts again, well, I don't remember that. Their yellow starts, wow, at 3. Okay, so 3. So recognize every single place. This is the German site. Their stuff is great because using HP, right, here's 30, meaning 30 minutes. You don't have to wait 3 hours. You can get a measurement every 30 minutes. You can also use HP 60 that gives you a measurement every 60 minutes. Okay, so you get a lot more bars per day, a lot more frequent measurements that gets closer to weather, but in still a convenient way of red, yellow, green, right? But be aware that they all define things differently. I think this is SWPC's. Yeah, 0 to 4 is, yeah. 0 to 4, actually, 0 to 4 was green in SWPC. Here, they turn yellow at 3. So get me? So I prefer this by a lot because it's much more accurate when it comes for aurora chasing. It's much more accurate when it comes to at least those who are like, I can't look at all those wiggly lines. Don't give me wiggly lines. Just give me something simple. So a start like a red, yellow, green, you know, meaning green, okay, don't bother. Yellow, ooh, maybe I should go. And red, yes, definitely look. HP30 is your tool. Okay, it's the best for you. And because it's planetary, right, notice the P, it's good for the globe. Okay, I do find that this is slightly, it varies slightly. These guys will oftentimes end up posting, and it may just be because of the time average, but they end up posting a higher number more rapidly than even just station indices in the United States. I still don't know exactly why, but I think it's still useful, very useful for planetary work. I think I don't think it's focused so much on Europe or anything like that. But it's something that you have to look out for, because I don't know all the details of how they calculate it. I don't think they do station weighting, but I don't know. Anyway, here's an example of it going up to 11, right? And I teased last time that these go to 11. So these go actually higher than 11, right? They go. I don't even know if there's a limit. They may even go higher than 12 if there were such a storm. Let's hope not. But a lot of these storms can get pretty intense. So it's nice to be able to see something not be capped at a KP of 9. And of course, this was the May event. It did get up that high, and it got up higher than that for a little while, I think. But it didn't last super long at that. It for the most part stayed just at what we call a baby G5, if there is such a thing. All right, and that is the end of the review. Okay, so hopefully that was a good review. That was a review of both. I'm going to put the chat up here for a sec. That was a review of both D1 and D2. We've gone over a lot of data products. You realize that? We really have. So we're about to jump into some really good stuff. Okay, I wanted to make sure, okay, I see a question here right away with a big question mark. Can you still get KP 0 day? What do you mean KP 0? As in the old system? You mean KP 0 data, Melody? SWPC, I don't know if they, I mean, you could get of course you can. I mean, you can get the raw data of the magnetometers that went into it. I mean, Intermagnet can get you that. So of course you can. It depends upon how you want it done. Like what specifically are you looking for? SWPC doesn't store KP data, sadly, on their site. So you'd have to go back to like NCEI or some of the other data repositories for that stuff. But you definitely can get data, pretty much any of that data. It's very well archived. Another fun way of looking at it is through the Bartol music diagrams too. Those are great ways of looking for climatological things, which I talked about when I did the ground-based series. So the G series. No, was it G? No, it's E series, E for Earth. I can't use G because G is, geomagnetic storm. It's a G level. I didn't want to encroach on any of those numbers, or those letters rather, for monikers for the names of the series. So look at my E series, and when we get to Bartol music diagrams, those are a really easy way to look at KP of 0 times, because it just archives it all, and it archives it very, very cleanly. They're just a different way of reading things, and I talk about how to read those. So if that's what you're asking, for a cursory look, great. If you want something more scientific, then you need to grab the data. And yes, you can find that in the Omni database. You can find it, lots of places. And you might even be more interested in DST if that's the case. So what's the G1 watch for? In the data that I just showed, this is truth. Was there or is there a G1 watch right now? And that's, if it is, it's for the CME the ICME that's hitting right now. I'm sure that's what the G1 watch was for. There's an ICME that's hitting right now, and last I looked, it was northward pointing field. I mean, I can check right now for us, just for grins. Wait, you're gonna go down? Okay. Let me take a look. I have Enlil up. Yeah, so this was the, oh, let me make it smaller, so, because we got the chat up here. I want you guys to be able to see it. I'll put it on this side. Wow, you didn't automatically resize, you silly thing. All right. This is for the storm. I guess I'll just do that. Yeah, you can see it now. Okay. This is for the storm that is supposed to be hitting us, you know, right about now. Or, you know, has been hitting us over the last day. So again, here's the live look at Enlil. This is our model right now, and you can see, you'll see a storm, a very slow storm launch. Oh, wait. Oh, I lost it. Oh, man. They updated it, those turkeys. Notice it changed. I'm like, why isn't it coming out? The storm, when it loaded the new one. That's one of the bad things about SWPC is that they change stuff pretty quickly. So there was a storm that was coming out. Wait, where's the 8th? It was supposed to be hitting right around here somewhere. And we did. We've had a storm hit. So right now, I think if there's a watch, it's probably for this fast solar wind that they're showing. We have a fast wind stream that's going to be hitting. I might as well show you the current model. But it's now no longer a CME model. You see ambient, so you know that it's just fast wind. So here's the fast wind stream that they expect to have it hit right here, and we're in it. And so that could be this SIR that they're looking at, right? Stream interaction region. I was hoping to show you the you'll see me, but they decided to update it. And let me get some solar wind. So again, I am just still at SWPC, so these are all data products that you guys should be really good at now. And oh, maybe it is just an SIR. Maybe it did miss us. No, that's a CME. No, that's a CME. So this, make sure you guys can see it because we got the chat up. Scoot over. Okay. This is a CME. How do I know? Because we're getting out to, this is the BY component. We're getting out to now, what, almost 15 nanotesla. It's pretty close. And I'm seeing a little bit of increase in the density, right up to about 10. But I'm not seeing any increase in the solar wind yet. 300 kilometers a second, though, that's pretty slow. I'll reserve judgment. Maybe it's still just an SIR, but I would not be surprised, especially seeing this rotation in here. This looks like there was a CME in this. Okay, so an ICME, which is intensifying this SIR. This is what I was talking about in a lot of my forecasts, and even the more recent briefing I did, live briefing I did a week or so ago. We're seeing that a lot more, right? Stealth CMEs are back as we move to the declining phase. Anytime you see coronal holes, you have to think stealth CMEs. They're around because they lie in and around the borders of these coronal holes, and they really lift off, and they're high altitude beasts, and so they just don't make much of a signature, right? So we talk about don't look at solar flare indicators for whether or not you're going to get an ICME. Stealth CMEs are a classic example of that, and when they're embedded in fast wind streams, well, they can give us a pretty decent plus up when it comes to magnetic field. The only reason why we're not seeing anything right now at Earth in terms of aurora is because that red line has gone northward. It's gone positive, okay? So amateur radio operators, maybe today's a good day because oftentimes northward pointing magnetic field gives you good propagation. The only thing I'd worry about, people at high latitudes, you're probably going to get some aurora, even with the northward field. It's just going to look different because we have a very strong BY, okay? No, we don't. Never mind. Shut up, Tam. That's BX. My pardon. My problem. Even I get confused what colors they use for BY and BX sometimes. So this is a BX component, very radial. Ah. Yeah, I think it's a CME. We're high impact parameter. Just trying to think, why would we get super strong radial? No, we shouldn't. Especially at 300 kilometers. That's a very tight Parker spiral. This is a CME. We're clipping through the envelope of a CME. Yeah. Because if this were just a high speed wind, we wouldn't, low speed wind, we'd have really tight Parker spirals. that means that the magnetic field would not be pointing radially toward or away from the sun. It would be very strong BY, which is kind of why I assumed that was BY. So yeah, this is we're going through the legs of an I see me. That's my perfunctory response to that. But that's why we have a G1 warning. It's because it could storm. If this went southward, if the red line went southward, we could see a G1. As long as this picks up. Solar wind's a little slow right now, but what's it at? So here's a you know, the only one of the few times that you will find me actually pause in the middle of a class and look at the forecast. Why? Because these are the data products we're working with, right? These are exactly the data products we're working with. So it's good, a good teaching tool. So yeah, 368 kilometers a second. You need about 400 kilometers a second to start bringing that auroral oval and opening it up and bringing it down to mid-latitudes. Okay, so just keep that in mind. All you people who are budding space weather forecasters and doing YouTube channels and trying to sound official like a scientist, it's so cute. I know a few of you who are really taken off doing stuff like that, and I giggle a little because I hope all these classes have helped. It sure seems like it. Okay, let's see. Hopefully that answered that question, right? So let me see what other questions we have. I think we need a D4. Already? I haven't even gotten into the good stuff for D3 yet. That's cute, Nick. Thank you. All right, I'll keep it in mind. You know, we can chat about it, of course. Monkey King says, cute name. Hi, Tamitha, what's your take on why NOAA's sunspot number and flux progression prediction models are so off for this cycle? Oh, is this normal for them? They're learning. Yes, I know why. And if Scott McIntosh were in the crowd right now, he would be going, woot, woot. They admit this, right? Their consensus is a group of a bunch of people that have had these long-standing models that have typically done very well. But as of about 2004, our sun threw us a crazy loop, threw us for a loop in the heliophysics regime, mainly the solar physics folks, which is not me. I'm an interplanetary person. But anyway, it decided to have what we call hemispheric asymmetry, meaning the northern hemisphere and the southern hemisphere decided not to communicate anymore or not be on the same side of things. And they had different ideas as to when solar maximum and when solar minimum should be. And so we started getting very well-defined dual hump, double hump solar cycles. And really what that means is one hemisphere went to solar max and then the other hemisphere went to solar max. That's why some solar cycles have two peaks and some solar cycles only have one. When you only have one peak, that solar cycle typically is much stronger. And it's because the two hemispheres are in concert. They're agreeing when solar max should be. But when the two hemispheres begin to pull away from each other, then the cycles become lower, less peak activity, and they become longer. And then you get a dual maximum. And so over the last several cycles, we've had really hemispheric asymmetry that's been pretty intense. And it's really messed up how a lot of the prediction regimes, the standard and the classic prediction regimes run and work. To a great degree, it broke them. But there was a crew that used to be at NCAR UCAR that now are working for Linker Space that really started looking at the sun in a totally different way. They didn't use sunspot numbers. They didn't use geomagnetic indices. They didn't even use statistics the way people typically do. They looked at everything on the sun. So this is filaments, this is coronal holes, this is bright points, this is all the different features, right? Sunspots too, but everything. And they started noticing patterns. And so they created an empirical model that didn't care what the sun's hemispheres were doing. It would look at everything. And they started recognizing how the two hemispheres are coupled, but they still have their own sense of things. And how that works, how that coupling between the hemispheres, how that works, ends up dictating a whole heck of a lot about the activity cycle itself. How strong it is, how long it is, how deep the minimum is. And so they put out a prediction that was radically different. And it was led by Scott McIntosh. And there's another group that's doing it somewhat too. They're thinking about hemispheric asymmetry, but the McIntosh crew have been really on it. So this is the stuff I've been teaching at Millersville since, oh my goodness, since I started the program. I have never taught any other way than what the McIntosh group have touted, because they're the only group that I've seen that has ever taken into consideration everything, right? Instead of just using this proxy and cherry picking this proxy or that proxy as a way to look at the sun's internal dynamo. This group, they look at everything and try to make sense of everything all at once. Now, it's not physics, it's not a physical mechanism that you're looking at, it's still empirical, still observationally driven, which is another reason why I love it. Observationally driven models, to me, when you don't understand the underlying physics, because you can't see into the sun's interior, observational, empirically driven models are the most robust, right? So I love them the most. And again, so this fit really into my bailiwick, and that's why the Macintosh crew have a much better model output than the consensus. And SWPC's learning to adopt that. As a matter of fact, Scott McIntosh is on the SWAG, which is the Space Weather Action Group that has been formed by SWPC. They physically said, Scott, we need you, and they stuck him. He's the solar the solar expert on that group, and has been for now. This is going to be his second term in the SWAG. So hopefully that gives you an insight as to why, and also gives you a good warm fuzzy feeling that just like everything in a growing science, you learn when certain things work out in a way that you hadn't expected. Well, you pivot to that side, and then you adopt the new things and move forward. And that's what SWPC's doing. So they're getting there. Okay. Hopefully that answered that. All right. The G watches for 210. Oh. Like I said, I've been busy making data products. I'm a little behind. I don't know. Maybe there's a new CME that launched today. Don't know. If anybody's got their eyes on the sun, let me know. I'm looking at the models, and right now, from what at least they've got modeled, they should be seeing something by the 9th. So it's kind of interesting that they've got a G1 watch for the 10th. Don't know. It sounds to me like they've got probably another, what you call it, CME. But we'll see. Okay. Melody asks, are you familiar with the work of David Lapointe? I do not know who David Lapointe is. What does he do? The primer fields. I'm sorry, I don't know what you're talking about. If he's an experimental physicist, I don't know that many. Experimental flat plasma physicists it's a laboratory plasma. It's different, very different. So is the KP automatically higher at night? No, because it's a planetary. It's averaged around the planet. So that means day side too. So it smears out things a bit. So that's one of the reasons why when I talk about aurora hunting, if you can go to different data products, like the advanced ones, we'll talk about some other ones, then do so if you're an aurora hunter, because KP is not going to serve you well. Typically, KP will tell you when aurora was 3 hours ago. HP is better, HP 30, but it's still smeared out because it's planetary, right? You want something that's a little bit, and it's also at whatever latitude, all latitudes, right? Be careful when I say that. It's really not all latitudes, it's lower latitudes. HP 30 is probably better if you're at mid-latitudes to pay attention to. If you're at high latitudes, it's ridiculous. It's not sensitive enough for you. That's why you go to things like AE. But we'll talk about that here in a minute. Okay. Any other questions? I was just reading Steve Thompson's thing. That's interesting. You guys are talking about layers of maps. Oh yeah, okay, good, good. I love the fact, Steve, I love that you're talking about this stuff. Yeah, and we've you've chatted with us. You know some of this stuff, so this is going to be wonderful to hear more of this conversation as we move back to Patreon and talk more about this stuff. Oh, Scott did check on. He did check in earlier today on my stream. Okay, I'll have to see what he texted me about it. That'd be funny. He can. I'm surprised he's not on here giving me, trying to heckle me. Let's see. Sounds similar to what Valentina Zarkova described when she was studying the sun. Yeah, but then again, Zarkova, she also expected that we're going to go into grand solar minimum, right? So, statistical physicists don't always know when they try to project into the future. The Macintosh group really does some unique analyses, and they've been really spot on. So, yeah, anyway. Okay. It's a crescent-shaped coronal hole. That's what so it's fast solar wind. Yeah, okay. All right, let's see. Any other questions on this, guys? No, okay. Awesome. Love it. I'm glad, Melody, I'm glad you got the answer, hopefully, that you were seeking. Okay. So, let's get into this. I'm going to take the chat back off. And here we go. Let's get into the next set of stuff. Okay, advanced data products. So again, these are just little things. All right, I'm not going into, there's just so much data. There's so many products that we could talk about. So I think I talked a little bit about Solar Demon. This is one of my favorites. This is, and what I'm going into is kind of the next layer where you got the basics down, right? So you know what solar imagery is. And now you want to explore maybe a little bit better way to use some of these data products, okay? Solar Demon is an excellent way of exploring some of this stuff. And why I say that is because it's still reasonably easy, okay? Solar Demon is looking at solar disk images, right? And it basically does difference imaging for you. And what's nice about that is that you've seen it like with coronagraphs, for example. When you do difference imaging with coronagraphs, you can really pick out the features. Like sometimes a coronal mass ejection in a coronagraph, you can't even see it in the raw imagery. But in something like a difference image, suddenly the halos will pop out, or a disk, the bright front of something of a CME will pop out. Well, the same kind of thing happens in these types of images. I don't know if I have okay. But it's not a very pretty website, right? Most websites for space weather that are created by scientists or a university group will not be pretty. Why? Because they're not web coders, and they're not doing it for the public. These sites are going to be less polished typically, unless they're big repositories. They're going to be less polished typically, and they're going to be designed for scientists, right, to be able to look at things. So Solar Demon's kind of very, very modest statement. They have some, obligatory statements up here that tells you what they're trying to do and what they don't have money for and what they hope to do soon, or, and you'll see sometimes a lot of things will be out of date, right? Because they were hoping to do something and then they ran out of funding, and now they just barely have enough funding to just keep their site alive, right? So they just leave it. Or perhaps the graduate student who was running it graduated, moved on, so the site just kind of stays right where it was, right? So you have these different things. What I always typically use is looking at dimming detection, or even better yet, all detections, okay? And when you go to all detections, or when you go to a detection, you'll see something like this when you actually pick one. I'll go ahead and go live to Solar Demon because I think it'll work. Okay, so there's the website. And so this is part of the lab aspect of what we're doing. Do I have Solar Demon here? Yeah, I do. Okay. So here's a live version of Solar Demon, right? Oh my gosh, it looks the same. And if I go to all detections, right? Yuck. Not very pretty, is it? Let's see if I can make it bigger. Scoot over. Oh, don't do that to me. Okay. Hold on while I make this cleaner. There we go. and I'll stand here. Okay, so as I make it big, right, it's showing you just the last detection. Okay, and it's showing it's a dimming. You can see a dimming's got a number. You see a gray disk, which is basically showing you where the disk is, and then it shows kind of a shadow of what changed. Okay, so again, these images will be grayed out, and then you'll see either black or white, okay, or shades of gray that are closer to black or white. Okay, just a plain shade of gray means nothing's happened. Right now, as you continue looking, you will see lists of all sorts of stuff. Okay, if you obviously it's kind of color coded in terms of light yellow means not much going on, orange is a bit more of a dimming, and then red is something pretty intense. Okay, so let's do this and see what it looks like. Oh, and you also have solar flares, which I'll show you in a minute. So give it a second to load. There we go. And now we've got something going on. Oh, look, here's that one of those big flares, and you've got a CME or something launched with it. Right. This one was, when was this? I can't see. The 8th. Okay, so today. So we had something go on. So here you can see, if I zoom in, you can see just the raw images, right? What we call intensity images. There was a CME. Now you've got dimming. So this is what we call a base difference image, meaning that it's a difference image, but unlike coronagraphs, that's what we call a running difference image. This image actually has a first frame. They start with a particular frame, okay? And it's going to be the very first frame that you see here, because it takes these images, these intensity images, and it takes the very first one and it holds it in a special place. It says, this is the frame I'm going to subtract everything from. So as the images stack up, as they continue to move forward, instead of subtracting one at a time, one next to its nearest neighbor, and then as you move to the next one, then that one gets subtracted from its nearest neighbor, and then you leapfrog in time like that. This one is, here's the first image, and then you subtract this one from its nearest neighbor, but then it leapfrog forward. This one does, but this one stays here. So then it subtracts a bigger subtraction, and then this leapfrogs forward, and now it's even a bigger subtraction, and then it leapfrogs forward, and it's a bigger subtraction. So what happens is this thing continues leapfrogging forward in time from one image to the next, to the next, to the next, to the next. Okay? This base image remains fixed. So the subtraction becomes greater and greater and greater, which means you see more evolution. How much has this image changed from this first one? Okay, that's a base difference. A running difference is how much has this image changed from its nearest neighbor, from the one right prior. So it catches higher, like, moving structures, right? So that running difference will capture things that are moving quickly, like blast waves or CMEs moving outward, right? Things that move quickly, wave fronts, stuff like that. A base difference image where it stays here and each image successfully gets subtracted from that base image, that shows you the extent of everything involved. Because over time, as whatever blast wave or whatever thing is moving across the screen and changing the image, moving across the image, this, by subtracting it from your base, it shows everything that has happened. It's like a cumulative thing. So it shows everything that has changed over that time. And so it's great not showing the front of a blast wave, but showing the entire blast radius, everything in that blast radius. Okay? So it's really great for that because it lets you see that. The only problem is it also keeps track of everything that's changing everywhere else too. So you have to be careful because you have to know what you're looking for, right? So as you take these raw images and you do a base difference imaging, okay, sure, you get the area of interest, which is this. See if I'll stand out of the way here, right? Because you can see it here. This is obviously the area of interest. So you get that, and you get to see a lot more. right? Look at that. All the way out here. You see, oh, this thing is really big. It blasts clear out to here, right? Boom, look at all that. Look at how much it captures. You'd never know that was the case here without, look at that. Looks teeny tiny. Looks like it's only this little bit. Actually, no, it's actually clear out to here, right? Because if I move to the base difference, look at all this. See what I mean? So base difference imaging is wonderful for stuff like that. It also captures surprises like this. What's this? What's happening down here? Right, if I keep it. So this was an ongoing eruption right here before this thing even blew. In fact, this was probably sympathetic. This thing might have even let go because this thing was already erupting. So you can see little changes in here. See how cool base difference imaging is, how it can be very useful to pick up stuff that your eyes may not have seen, right? The downside is that it picks up lots of other stuff too. Oh, look, there's a far side eruption up here. You got stuff coming off up here. Oh, look, you got junk coming off over here. There's junk coming off over here. These loops are changing. There's lots of distraction. Looks like growing little worms everywhere. And then, of course, the absolute change shows you. Ugh, what a nightmare. Look at all this stuff. This is an area of interest. This is an area of interest. What is all this junk up here? There's all sorts of other stuff. Look at this one that goes flip, 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 flip. Flutter, 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 flutter. Because there's something that's fluttering in here somehow. Something's lifting off, like a blast wave or something. Or something maybe in this image, the exposure's changed. I don't know. I personally never look at this thing unless I'm really stuck. I'm looking at this and so I just want to see what? I don't end up using that thing for anything. Now, you can actually, just so you know, you can actually click on this more. And you get this. Get out of the way. This is really nice because here's the running movie of this eruption. Here are some of the light curves. And what's nice about that is if you put your cursor over this light curve, look, you can make this movie move. And so if you want to swing something back and forth to say, how big is this? What is it doing? How is this moving? What is this? What's going on here? You can do it this way. As a matter of fact, you can even see in the light curve, specifically when it starts, see the bump up? Where you get that real big explosion, real big explosion up. And so you can see that blast. You can even see that little blast wave here. It's part of that weird ripple. Boof, there. And then where it stops, where that's a big part of the solar flare that occurred. Okay? And so you get a chance to kind of more quantitatively, not just control, but more quantitatively see what it is that you're looking at. Okay. And then you can just go back and you can, if you really want the actual images, you can download them. So you can create your own movie if you want. Right, it's got them all. Isn't that nice? And you can do that for any of these, right? More. And you can also go backwards in time if you want some of the more of that information of the data, right? Which is useful more for either automated algorithms, if you're trying to automate or if you're trying to put something in a physical algorithm because it's quantitative, or if you're a scientist, right, trying to look at stuff. It's great for statistical analyses of these different things because you've got a solid baseline. Now, caveats. Sometimes Solar Demon will overemphasize. I've been warned that sometimes it will overemphasize the dimming. For the most part, it's pretty good. Operationally, I think it's wonderful. I've very rarely been misled with Solar Demon operationally. If you want to do scientific analyses, okay, that might be another story. Right? But operationally, to let you know the extent of something, whether something is useful or not, you know, like coming toward Earth or not. Like for me, I would go back and take a look at this and look in coronagraphs, because this is an event today. This could be a CME that NOAA and NASA are actively modeling, because this does look like it's probably an event that launched. The biggest problem that we'll have is that we have this second event here that actually launched first. That will probably camouflage this one a little bit to make it a little bit harder to know how big the part of this that's coming toward Earth, if there is a CME that launched with this, how big that is, because it's going to be caught up inside this higher latitude structure. And maybe as we look at it, we'll see that it was all part of the same thing, and it left from here first, and then the rest of it came off, you know, so to speak, or I say it this way, left this way. We'll see. What else do I want to say about this? I think that's it. So hopefully this is a really easy tool to use, okay? That should help you understand that every whistle and fart that the sun makes, pardon my language, isn't a CME, isn't an eruption that is going to launch a solar storm. Because there's a ton of people out there that every time the sun blinks, they're posting, oh, new eruption, oh, check a look at this, oh, look at that. And it's like, what are you doing? It's not important. It's nothing happening. And so they get burnt out. And I don't want that. I don't want people getting burned out, posting every little thing that the sun does, and then finally just going, you know, I'm tired of this, right? And then they lose interest in space weather altogether. No, just do some due diligence and take a look at some of these base difference images. For those who are in the know, yes, these are derotated. So if you wonder, if you look over a long period of time, why isn't the sun rotating? They've derotated it, okay, which means that it's like they froze the face of the sun and it's not continuing to rotate. So you're not going to smear out these, as far as I know, it's derotated. You're not smearing out the event horizon, so to speak, in longitude, because the sun is continuing to rotate as this base difference imaging process occurs. They've derotated it, frozen it, so that whatever longitude was at, you know, that Earth was staring at, the sun stops there. It's a mathematical derotation that when we go into J Helio viewer, which we probably won't get to today, we can do the same thing in a pretty clean way. Okay, hopefully no more questions about Solar Demon, but like I said, it's a very useful tool. All right, Stereo Science Center, another really huge one. It's important. Of course, there's the website, right? And it'll look like this when you go there. Here's other views of it. You want to get to a sidebar where you can see different aspects, latest imagery. Those will be like latest images and plots. You also can find when it says where is stereo, that gets you to the stereo orbit tool that allows you to, no, come on. There we go. That allows you then to look at different space weather, different products. I'm going to kill solar, well, I don't know if I should kill it or I'm just going to go back so it stops working so hard. And I don't think I forgot to get stereo up. I thought I had it up. Guess I didn't. All right, so here's a live view of it, right? So typically latest images and plots. If I go to latest images, the nice thing, you can go to the stereo image search tool, Movie Maker. Of course, you can see this, right? If we had stereo B, we would be able to have the entire field of view. Poor stereo B being gone means that we only get, you know, a little bit of the whole Carrington view of the sun. But hey, at least it's bigger than it used to be, right? We're getting more imagery of what our star looks like thanks to stereo A. Here's the coronal hole, for example, that just gave us some decent fast solar wind not too long ago. It's now partially on the far side, right? And you can see some filaments that stereo A is able to show us. And that will become more interesting over the next couple of years as we get away from solar max. So here is the movie maker. And when you're looking at it, as you can see, there's still behind stuff, because the reason why is because you can go back in time to when behind was actually available. But obviously, if you try to search for anything past like 2015 when it died, you're not going to get any data, right? But so you have the ahead vehicle, you have the behind vehicle, and you have EUVI. These are all the ultraviolet, extreme ultraviolet wavelengths, right? If you want beacon data, which is the forecasting stuff that we use, the lower resolution, the only way you get it is through 195, the green sun in this case. Not the same as the green sun in SDO. The numbers change. In the closest wavelength that we have in SDO is actually painted bronze. Okay, it's the bronze sun, 193 angstroms in SDO AIA. But here in stereo, they painted it green. Okay, basically the same wavelength. This is where we get the low resolution imagery, but it comes almost in real time. Okay, very, very quickly. You want higher resolution imagery, you can get for everything, but it's usually 2 or 3 days behind. Why? Stereo has a very tiny, tiny telemetry pipe. It's not that the spacecraft is old. I'm so sick of hearing that. I would just like to throttle people who think that that's why stereo beacon data is not good looking. It's not because the imager is old. Stereo and SDO were launched almost exactly the same time. So no, it's not that at all. It's literally because stereo's pipe is small. Okay, so start and end times, let's do 0208, or no, 807, and 2502. I'll do 09 if you push the date. When you're putting start and end dates, if you push the date out a little bit, you'll be sure to get all of the imagery. If you want a movie, you have to hit slideshow. Otherwise, it gives you image, 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 image. It's like, oh. You can download them all if you want, or you can just get a list of images, right? And then you can skip images if you are trying to get too many and you don't want every single one. Just leave it blank if you want everything. Look at that pretty stereo stuff. It's getting useful again. I love that. Pretty soon I'll be able to use the far side monitor, because what was at Earth, right, what was something that was happening over here is now happening in a different place for stereo. So that's really nice. Not quite useful, not quite super useful for far side stuff yet, but as you can see, the resolution of the images, right, is down. That's because it's beacon data. If I were to go back in time, for example, go back to what, maybe the 5th, so February 5th, let's see, and well, I'll leave it, I'll make it to the 7th. We might actually watch, yeah, so we can see, as soon as it finishes loading, it's got 600 images to load. That's loading pretty fast considering I'm on this stream. Very happy. There's science grade data back on the 5th. Let me make it go faster. You'll tell. Ooh, that was a nice, pretty filament eruption. That's back on the 5th. Science grade data looks really nice, right? You can be able to tell when it goes to beacon data. I guarantee it. Science grade data also has higher number of frames, so you can see the cadence is better. When it goes to beacon data, good Lord, you never know what you're going to get, because it skips frames, it'll backfill, they do all sorts of stuff as the data comes in for beacon. But they try to get a decent enough amount of data down so that you can actually do forecasting with it. Because what good are high rate science data images for a forecaster if we have to wait 3 days or 4 days to get them, right? The CME, anything we would have used them for would have already been here. So this may starting the 6th, there you go, you can see it. See how much rattier the data is? See how much faster the sun is rotating? See the skip frames, right? Not because the spacecraft is old, but rather because it's beacon data. This is science grade data. There's science grade data. I just sped it up a bit. Come on, get to the beacon and beacon. Okay, science. I can make it really, really silly. Make it a really silly thing. Beacon, science. Do you get me? Does that make sense, guys? So this stuff is used. This is the stuff that scientists use. The beacon data is the stuff that forecasters use, because we don't care so much about the quality of the data if it's good enough to let us see what's going on, right? To let us forecast what's going on. We can always go back and get the science grade data later. Okay. So if you ever wonder why you're seeing that, it is literally, it's a feature that we were so grateful that the stereo science team was smart enough to do. Janet Lumen, I think, was one of the ones that argued and really advocated for beacon data. And I'm forever grateful to her for that. Hopefully she hears me. And I just love her to death. She's a PI on the SECI, and that's right, SECI. And she was very instrumental in making sure that forecasters were part of the conversation, even though this was a science mission. So this is why it is that way. So anytime anybody tells you that it's because stereo is old, let them know that they are misinformed, because that is not the case. Okay, does that make sense? Hopefully, everybody get that. And then the other thing is, if you go to where is stereo, right? And I'll show that in a sec. Let me go back before I show that really quickly. The reason why is because you can also get coronagraph data, because stereo has a chronograph. Its chronograph is not as happy. It had some issues with its mirror when we built it, sadly. And you can't fix stuff once you launch it, right? So you got to just deal with it. Core 1 is almost useless. Core 2 is better. And so what we oftentimes do is use Core 2. RD is running difference. Remember we were talking about the difference imaging? Right. In this case, it's a running difference because you want to be able to see that stuff. Yeah, and I'll do the same thing. So science grade images, and then you'll see beacon right there. Okay, science grade images in a running difference. So you see lots of CMEs coming off. And you'll see the beacon. You can tell that suddenly it becomes really ratty. Okay, hold on. Let me go faster. Make it run faster. There's beacon. See how much rattier it looks? Right. So we have that for all of the imagery, but it's important. And why is this? Why do I say when we talk about this now? Why is it important to know where stereo is relative to Earth? Ugh, I don't like that one. Because it lets you know how far out it is, how much of a different view. Earth is getting a view right here. The disk that it sees is why I use the phrase disk. It's a flat disk that it sees. This round thing is flattened into a plane that lays on top of my hand. That is the solar disk from Earth's perspective. The solar disk from stereo's perspective is perpendicular to its line of sight. This is the solar disk from stereo's perspective. So a plot like this gives you a good insight as to what exactly we see compared to what stereo sees. Okay. And as you can see, there's also other spacecraft. Here's Solar Orbiter. Here's Parker Solar Probe. These are locations where these spacecraft are. You don't have to plot all that junk on there if you don't want. But if you go to the Stereo Orbit tool, it's a great little tool. I'll do it. You can also get the data here, but I'll click on Stereo Orbit tool because it'll give you a simpler picture of where stereo A is relative to Earth, much further out, as you can see. Right, so now you don't have all that junk. It's showing in the inner heliosphere. Pretty soon it will expand its view because stereo A, as you can see, is almost out of the frame, so it will automatically adjust. But the nice thing is that you can also get all of this information. You can adjust the plot. And there's lots of other places to do stuff like this, but this is a nice one. It's convenient. And they've always been very good about keeping this thing running. There's only been a couple times when it didn't do well. Terry Kucera is a wonderful person. She's a really, really nice person to know. And very savvy. Okay, I'm trying to think, is there anything else? You can also go to get data. Imagery is a lot easier, but you can get data. There's archived data from all sorts of stuff. Like I said, way too much to go through. But if you do browse data, then you can actually do, we're back to that stereo movie thing, but you can also browse images and plots. So you can look at solar wind, very similar to what we have for ACE and Discover. Same kind of idea. The difference between X, Y, and Z is now it's located at stereo. So you pretend that stereo is like Earth, and you're getting that same data, but now that coordinate system is going to be, pointing at the sun from their perspective, right? So you couldn't do apples and oranges comparison because it's slightly different. But because the sun's magnetic field and solar wind is moving out radially, there are certain comparisons you can make. But it's not exactly the same. It's also in the RTN coordinate system, which means that the T component, which they call the transverse component, which is akin to our BY, is actually reversed. Negative is positive, positive is negative. So what is a positive BT is a negative BY from our perspective, if you rotate out. And I'm not going to go into the details of that. You can look up the RTN system and see how it differs from GSE or GSM and understand the details why, but that's a very advanced topic. Most people aren't going to be looking at stereo data unless you're trying to figure out whether a CME has hit us or missed us. And from that perspective, then you can easily tell. You don't have to know the details of the coordinate systems. Okay. All right, let me get back to this, because I think that's about it for stereo. Okay. Now let's talk about ROTI. Okay. So now we're going to jump into the ionosphere a little bit. So one of the advanced data products that I like to use, as you know, because I'm creating a data product for it, right, the ROTI system, comes from the Ionosphere Monitoring and Prediction Center at DLR. Okay. A lot of good sites are German. And of course, they're going to have things that are focused on global as well as Europe. They're not going to have things focused on the United States because Germany's not in Europe. Germany's not in the United States, it's in Europe, right? So that's the thing about a lot of these, especially the advanced products. They're going to be focused, their focus point is going to definitely be mainly where their country of origin is, all right? But oftentimes they'll have global products as well. So they've got multiple things. There's lots of good data products here. If we go to a live version, well, I'll show you that in a sec. Go to a live version in a second. Here is their ROTI map. Okay, it's in a familiar system, right? This is that same squished. It's not the Mercator projection that I like, but it's a flat. I forget what the name of this projection is, but it's the same projection as DRAP. So it's useful for comparisons. But their ROTI, as you will see very shortly, their ROTI, they don't smear it out like I do. They keep it in these 2 by 2 degree pixels. And so it's very spotty, and it changes quite frequently. And to me, it's kind of hard to read because of that. And I think do I have that up on this one? No, I think I have it on this one. Hold on. Oh, pain in the bum, makes me sign in again. Hold on one second. Where are you? There you are. Okay, let me switch and show, because what you get with, hang on, come on, I can't think in, uh-oh, it's not switching, what's happening? Oh, because, no, that's not right. Oh, that's why. Hello. You got to press the right button, Tam. Okay. So what they do is they only give you, if I can make this the right size, come on, give me a break. Okay. What they do is they only give you a single slide. So what I like to do is I like to, let me make this longer. Let's do a full day. I capture these frames and make them into movies because to me a movie is, well, it's going to take a second. As you can see, 5%. Movies are far more telling, right, than just still images. Still images are great, but who has all this time to sit there and stare at a map of little bugs flying all over the windshield, which is kind of what the way that when they map these is kind of the way they do it. Now, what you will see with ROTI, again, this is kind of like the rate of total electron content, how it changes. It's not just a gradient, though. What they're looking at is when you get these signals, they can deviate, like change a lot over a short period, and that's due to scintillation, things like scintillation. And they capture how much of a deviation that is, okay? And they look at standard deviation, how much of a spread is that? That indicator, if it's a super big spread or a smaller spread, that indicator is what they can call ROTI, okay? So when you have a big spread, then you get red. When you have a very small spread, then you get green. Okay, and so you've got this bar that comes up. What I've learned just in the last 24 hours of working with the data itself is that the max ROTI goes way higher than 2. I have my screen on the Geochron set for 2, but the max ROTI is in the thousands sometimes. It's like, okay, some of that has to be anomalies, has to be artifacts, can't be real. But nonetheless, so I hard limited it just like they did at 2 to show how many units, TEC units per minute are changing. And anything above or anything around 2 is going to be considered red. So as you can see, their version, they're keeping it, the geographic parts of it really locked in, and it's changing quite quickly. For me, that's a little bit hard to read unless you've got something that is a trend that continues, or something is more longer lasting, right? And then you can kind of see it because the colors don't blend, but you can see that this actually has a red peak, kind of yellow, and then fades into green. So it's an actual, region in here that has got some level of disturbance, not horrible, but something. Notice all of these little bees, okay? These are all places where we have receivers to be able to scan the sky and look for GPS. So you don't have them over the oceans, okay? And so they've kept it very localized so that people don't so they don't see what I see in the map where you've got this big swath of red, because it's probably not true, okay? And I've got to figure out how I want to handle that, right, in my maps. But I don't particularly like the buzzing bee look. To me, it's extremely dizzying and it's not very insightful. I like things when they're a little bit softer and smeared and give me contours. Don't give me buzzing bees. I don't know what to make of that. Especially when we have a geomagnetic storm, about the only thing you can see is kind of a line where the auroral oval comes down. It's all red. And that becomes really nice, and then it recedes. But when it's just minor disturbances, it's harder to tell. So again, what you're looking at are areas where scintillation, the risk for scintillation is high. Why? Because all of these red parts, these little red bees, are showing you locations, what we call pierce points in the upper atmosphere, where GPS signals have been wonky, okay, for that period of time. That's why they disappear quickly, because either the GPS spacecraft, the signals are lost, or the scintillation that was occurring didn't last all that long. Now, this map does not have, as you can see, does not have a terminator. Doesn't have terrestrial weather on it. Doesn't have anything to give you any inclination, any understanding of what this might be connected to. And so that's why I think the Geochron is a better solution, because you can integrate it with so many other data products that give you more insight as to why you might be having scintillation or having a high scintillation risk in certain areas. If you remember the Geochron map you could actually see that scintillation or potential for scintillation was much higher on the night side of Earth, wherever that may be. They don't have that on this map, sadly. I think their map would, if I could give them a hint, a shout out and go, hey, put a terminator at the very least, put a terminator on your map so that we can see which one's day or night and people can tell where dawn and dusk is. It matters, right? The next thing is to do, TEC, the actual, so you could see the actual equatorial anomalies, which stay, or the equatorial anomaly, the Appleton anomaly. Through here, you can see where these bands of enhanced electron content exist that typically cause problems, cause scintillation problems. But this map is available for you, right? Like I said, as a single image that updates once a minute. If you want to make a movie like what you're seeing here, you actually have to do that yourself, okay? But sometimes you see me use these. From now on, I'm probably going to be using my geochron. Yay! But this is the source of the data. And so use carefully, right? You shouldn't use data like this to inform any, all decisions. But if you come into trouble, like if you're wondering, why am I, everything else checked out, why am I still having trouble? If you're a radio operator, for example, you might look on a ROTI map and see if your area is having high scintillation, especially if you're more low latitude, or if there's a big geomagnetic storm, and then you can see stuff going on at high latitudes as well. Okay. But it's a very useful tool, and I think, again, it's one of those things that becomes even more useful when you combine it with other either terrestrial weather data, space weather data products. Okay. All right, let me go back. All right, let's go back to our thing. Okay, so this is what it looks like on the live site. Right, you'll just see this. This is also in the ESA. I think this is in ESA. In their space weather portal. I don't know if they even have the global. They may only have Europe. But if you go to the Europe one, it blows up Europe really big. And so you get higher resolution for Europe, which is nice. Okay. And then there are other certain things that you can find. The WAM IPE model also has stuff like this, but these are all done through observations. They're empirical, which I love. It's not a model. This is actual data. Okay, so that's the nice thing. This is where this stuff is actually happening, not where some model thinks it might happen because, well, the data looks like it could. This is where things are actually happening. All right. Another good one, which sadly we can't really probe right now, is Kyoto. Kyoto is partially down. But one of the things, it's, again, another scientific style website, really ugly front end. Right. Welcome to space weather. This is a huge data repository. We will not go over everything in it. I might mention a few things about it. But one of the things that is really useful is the AE indices that it has, real time. And it has not just AE, but it also has DST. It has ASIM, which is another faster product like DST. These are all magnetometer indices that then, or data from magnetometers that then can be turned into indices, like KP, right? The AE, what's nice about AE is that, unlike KP, it's focused more on the high, in what we call the subauroral region. So it cares far more about the electrojets, the east and west electrojets. Just like we have a jet stream, these are the space weather equivalent of the jet stream. So we have an east and a westward one. And they are essentially right around where the auroral oval is. So when the AE index and its sister indices go crazy, we got aurora, especially at high latitudes. Okay, and that makes it a lot more sensitive than KP. But with that being said, the problem with AE is that it becomes overwhelmed during big storms. Okay, and it's especially the real-time, the forecaster or the nowcasting version of them, the plots become very ugly during big storms. So you just have to be aware of that. Here is what the AE suite looks like. The AE index is this last one down here. It's basically taking the upper index and the lower index and subtracting them to get the envelope, and that's what E means, I think, the envelope. So this upper line is the value of that envelope. Here, the upper line is the upper index, the bottom line is the lower index, and like I said, it's getting the envelope, it's getting the value of these. Okay, what is the difference between them? And so it can see different things, even though in this case you had like really low numbers in here, right? AE still looks big. So that's really nice the way it tells stories. The bad thing is that it can get really ratty at Kyoto during really big storms. So here's the 2003 storm. Look how ugly. As I've said before, when we looked at this in the E series of courses, the Earth series of courses, where I'm talking about lots of ground-based indices, the color is not the intensity of the storm. The color is how many stations are reporting in. Okay? Sometimes you have less, sometimes you have more. Right? It all depends upon what's happening. This is an old storm, so a lot of the stations have reported in. Back in 2003, they got lots of stations in. Here, I think I grabbed this when it was happening or shortly thereafter, so not all the stations had reported in yet. Okay, so keep track of that. If you see things that are, green, then you've not had that many stations reporting in, and you got to wait a little bit longer. And you'll typically see that when you're looking at the real-time data. You'll see the front end of the leading edge of whatever it is will be multicolored because the stations are reporting in one at a time. But it gives you a way to keep track of it. So that's what the colors are. It's not how intense the storm is. Okay. Sadly, right now, the AE index at Kyoto is down, and I have not been able, I've been so busy in my own little coding cave that I have not reached out to people to find out what's going on. So some of you might even know what's going on, and I don't. Just really quickly, we also have DST. DST index at Kyoto is not very good looking. It literally shoves everything into this tiny little bar. So most storms just kind of rattle around here. You have to have a really big storm to make things look good, to give you any type of deviation at all. Not my best way of looking, not my favorite way of looking at DST, but good for a quick look. Kyoto also has plots for its magnetometers, which is really nice. You have to look at where the magnetometers are, right? But they all have their designations. If you're a satellite operator, these are kind of like PNT numbers, identifiers, right? So those are useful, but beyond the scope of what we're talking about. If I decide to do something like a deep dive into geomagnetic indices, geomagnetic magnetometers, like actual looking at magnetometer data and substorm data, or looking at ionosons, that kind of stuff might come in. Okay, so hopefully that's a good enough walkthrough of that. Now we're going to quickly take a look at other data that's useful. University of Delaware, the Bartol Research Institute. This is an excellent place to get cosmic ray data. Okay, and we're going to talk a little bit about it. I'm not going to go too far into it, but just some people get cosmic ray data. They like looking at it because cosmic ray data can tell you where Forbush decreases are, mainly. This is where spaceship Earth exists. And I have gone over this stuff, again, in this case, I've gone over it during radiation storms. So that was the Peace series. We talked about cosmic rays because we were talking about radiation storms, and cosmic rays are a type of radiation storm. They're just not a radiation storm from our star. But cosmic rays are super important because when they disappear, that tells us we're in a magnetic bottle. And that magnetic bottle is due to an ICME. In fact, if we look at it in real time, we might actually see whether or not we're in an ICME, right? We talked about, hey, we're close to something. We'll see if there's what we call a Forbush decrease. Here's an just example of the real-time cosmic ray stations that you can get when you go to Bartol. They've got them running. It's wonderful. Here's examples of up, down, the ones that you can plot. This is probably Ulu. Yeah, Ulu's a workhorse. Here's something that looks like we're getting down into a Forbush decrease, which is basically where the cosmic ray flux really drops more than just a few percent. Notice this says up and down in percent. Okay, so this dip is 5%. That's a big dip. If you see it dipping more than 2, then you're probably in something close to a Forbush decrease of some kind. What that means is you've got a magnetic structure close to Earth, in and around Earth, that is shielding out cosmic rays from hitting Earth. And so the cosmic ray flux, or the neutrons that are being detected, are going way down. Okay, so it's kind of like a way of probing what's going on outside. Kind of like this. So imagine if you have a CME coming at you. This is a magnetic structure, and as it grows, right, let's say it envelops Earth like this. Terrible drawing of the magnetic field. Don't pay any attention to it. Just know that this is like a magnetic bottle that we're now caught in. Before, cosmic rays come in at all angles. That's what this diagram is trying to show. They're coming in at all angles. But when you get inside a magnetic bottle, this is a closed structure. Its foot points are at Earth, at the sun, rather. And so the cosmic rays have a tendency not to be able to penetrate very far. They kind of spiral out. And so this is why Forbush decrease happens. So you can imagine that even if we're not inside this structure, but this structure goes nearby Earth, it's going to shield out successfully cosmic rays at least on one side of us. So even if we don't see the signature of the CME at Earth, or the ICME at Earth, right, we'll still see a Forbush decrease, showing us it was a near miss. And yes, indeed, it was a big ICME, or a big shock from some fast solar wind that's moving by. Because shock waves also kind of act as shields because they're magnetically strong. So you can get these really nice galactic cosmic ray depressions as a Forbush decrease. Here's 3 different stations showing similar traces. Okay, this was during one of the massive set of events during the Halloween storms. When you see ups like this, they can correspond to radiation storms from our star. Okay, and those are what we call ground level effects. That means you have to have a really strong radiation storm from the sun to actually make a dent in what you're seeing here. So he had a nice little bump here from one radiation storm, nice little bump from another radiation storm, and even a third radiation storm that impacted only 2 of the 3 monitors at that time. Not every monitor is going to follow what the other ones do. As you can see, here's a classic example of monitors not being exactly the same. And that's something you have to be very, very, very careful of, okay? Ulu is a good monitor to choose because of several factors. The main one being that lower energy particles, lower energy cosmic rays can reach Ulu, whereas some of the ones at lower latitudes, they're more shielded, so they're harder to see things like Forbush decreases. And the reason for that has to do with something called a geomagnetic cutoff. If you look at, and I'm not going to get you, don't worry about this. I've talked about this in the E-series, where if you're at 0 degrees latitude, you're at the heart of the Earth's magnetic system, where the magnetic field is the strongest, what we call low L shell. So you got really strong magnetic field in this region. That shields out cosmic rays. But if you're at the poles, at high latitudes, well, the magnetic field is open. So you actually get unimpeded cosmic ray bombardment. Did I say that right? Bombardment. So you can get a lot of shielding. Your count rate will go way down. So it's going to count rate up this way. So if you're looking at these lines, don't worry, it's solar minimum, solar maximum, 2 different times, but let's not worry about it. Just know that they both go way down if you're at lower latitude. It doesn't matter if it's north or south, it goes way back up. Here's 90 degrees south latitude. 0 degrees, cosmic ray flux goes down quite a bit. Okay. High latitudes, if you go back up to high latitudes, cosmic ray flux goes back up. Up, high latitudes, down at low latitudes, up at high latitudes. north or south, because the poles are open. You don't have a strong field here, you have a strong field here. Okay. So what that means is that when you look at all these different monitors, there's tons of them all over the place, certain ones won't get as high of readings. Right? Darwin, for example, doesn't get anything. Well, it does, but just it has to be really energetic stuff. So where's Ulu? Pretty high, right? Apatiti's even a great, I love Apatiti. I love South Pole at McMurdo, but sometimes this one's shut down, sadly. One of my favorites. Ulu and Apatiti are great ones. The other problem that you have, too, is if you ever decide, if you're going to look at cosmic rays from neutron monitors, is that if you say, okay, well, the cosmic ray monitor is here, so it's seeing what's ever above it. That's not really true. And you say, okay, so that cosmic ray came from there. No, that's not how it works. Cosmic rays have these massive spiral patterns and paths. And so you may be thinking you're looking out like this, and the cosmic ray shower that's hitting you came from cosmic rays over there. You're like, how the hell does that happen? It has everything to do with what we call an asymptotic viewing cone. And I won't go into the details. I talked about this in the E series. But you can have, for example, and this is a terrible drawing of a magnetopause, right? Someone who doesn't know what the Earth's magnetic system looks like, they just drew a ball. But what they're trying to say is that depending upon the energy of a cosmic ray and the location of its being viewed, you can have the station literally see almost straight up from where it is. So if you were to map this, the cosmic rays that come down, they get filtered because they're spiraling in. And so you get this cone of view that's then focuses down to here. Well, if that's Barentsburg at this time, whatever local time you're at, that will focus in on a place that's pretty close to where Barentsburg actually is. But that's not always the case. Look at Apatiti in this case. Here's Apatiti. But look at this smeared out thing that goes across the equator. If you were to go out to the Earth's magnetic, the boundary of the Earth's magnetic system, cosmic rays that are entering near the equator on like the dusk side of Earth or something are coming in. They're all smeared out depending upon their energy. They all get funneled in to Apatiti. But if you were to map that down to the planet, look at it. So Apatiti is measuring stuff that it thinks is way up high. But in actuality, it may not be. Okay? It may be coming in from a totally different place. So that's more important, not so much for Forbush decreases, but it can be. It's more important if you're looking at radiation storms from our star because they're far more directional. But nonetheless, be very, very careful. Okay, it's a cautionary tale. Be very, very careful if you're using cosmic rays to try to make any quantitative understanding or gaining any quantitative understanding of what is going on out there. Okay, they can be very, very deceptive. So use it carefully. Take everything that you learn from cosmic ray monitors with a grain of salt because they're tricky, tricky, tricky. Okay, and it gets even worse because asymptotic viewing cones, which you can see here when you see sometimes if you ever look at maps with asymptotic viewing cones on there, that'll be the line that kind of shows where they are, and some of them will be in different places, right? So you'll see the actual monitor here, and then you have to go search for the asymptotic viewing cone, and that's this here. So here's Norilsk, and then here's the viewing cone for Norilsk. Okay, so you can do this, play this game all day long, but the sad thing is that asymptotic viewing cones change. So here's some viewing cones, and if you look at this map compared to this map, they're different. Why? Because you constantly have to recompute asymptotic viewing cones based on the rotation of the Earth. Okay, I went into this in detail in the E series. So this is just letting you know cosmic ray stations they are non-trivial, especially when you want to compare them to one another. Do any science or do any even forecasting or nowcasting with great care. And don't think that you can see more going on than you can. All right? But that's a good place to get them. Let me see where I am. We've gone through a lot of slides, guys. We're in slide 58. That's pretty good today, huh? Okay, let me do two, like 3 more slides, and then we'll pause, and we'll decide if we want to do any more. Okay. So a couple little last minute things. Here is stuff that's sadly only good for the United States. Okay. This is basically for transmission lines. So it's actually good for the United States and for Canada. This is using magnetotelluric assays that the USGS did to be able to tell basically what the ground conductivity of the Earth is in these regions. So basically, what is your bedrock like? Does your bedrock? I'm just kidding. But what is it like? What is it, what's it made of? Is it conductive? Because if it's conductive, well, then the chances of you having GICs, geomagnetically induced currents, are bigger. Because if you can liberate more electrons to move, then they will. And they will move through the lines and all that kind of stuff. So with these maps, I don't think this one does. I think I have the next one though. Okay. With these maps, what you see as this thing loads, this is just a version from, I think, the May 5th event. Is this? Or the May 10th event? Yeah, 10th and 11th. I don't think I got the 10th, but I got the 11th. What you see is areas where you've got really strong currents coming, okay? And grid people probably watch this a little bit. They know. They don't need this map to know when they're having trouble. When you get above about 10 volts per kilometer, and to be totally honest, Auntie Polkinen says 8 volts per meter or per kilometer. That's when the grid, the grid players, the utility companies begin to really get concerned. Okay, so most of the time, as you can see, even during the G5, the values are pretty low. I mean, not pretty low. There's times where it gets up there. But this G5, this is why I call it a baby G5, is because it wasn't, even though the grids didn't necessarily like what they were seeing, it wasn't the end all, like grid killer. If it had gotten a bit stronger, though, I would have been worried. But we were okay. And so that's a good thing to monitor. We also are spreading it out now, doing some for Canada. As you can see, it's not quite of high resolution. This one is still, being developed. So the grid has to be, the grid size has to be broadened, because I don't think we've mapped as much of Canada as we would like. But we're definitely in partnership with their geological surveys and trying to get an idea, because we have so much interconnectivity between the two regions, and our utility consortiums really are no longer independent of each other. And it really helps to be able to see what types of loads are coming down from the north, so to speak, when it comes to some of these these potential, these field potentials. Okay, so that's something that you can watch. I do know heliobiology people also care. If you find yourself very sensitive to electromagnetic disturbances, you might pay attention to something like this. If for no other reason, then you will know if things light up like a Christmas tree in the area that you live, and you're wondering why you have tinnitus, or why your head is hurting, or why you can't seem to form a sentence. These might be why, or why your heart is pounding, right? People with cardiovascular issues that have these comorbidities that make them sensitive. This is not necessarily a bad place to look. But of course, again, it's limited to the United States and the Northern Hemisphere. Okay, but just know I know people personally who are using these as off-label use. They don't use them for the power grids; they use them for their own benefit. Okay, anyone who has mercury blood, heavy metal poisoning, anybody who gets rashes on their hands every time they use their cell phone. I mean, there's lots of people who have plates and pins and screws. These are people who and their bones ache or something like that when there's a big geomagnetic storm. These types of maps might actually be useful to you. Okay, as we're learning more and more about medicine and medical research when it comes to health, there are impacts, and some big names are beginning to pay attention to it. There was I don't know if some of you know, there was a very interesting YouTube video done by the folks at Earth Sky and some people from NASA. And it was very interesting to watch, to see them saying, there might be something to this, because they're seeing places like Harvard, right, Boston College. They're seeing big institutions with reputable names, not only as the physicians, but also heliophysicists and geophysicists on their author list, their co-author list. And they're seeing more and more of these papers come out. It's because there really are impacts. But just like everything else, just like I said with stuff earlier, space weather typically doesn't act alone. It's not something that will cause a big crash or horrible thing by itself. But if you have all these comorbidities, right, it exacerbates existing problems. And depending upon what those existing problems are or how exacerbating the issues are, right, then that can take a mild situation and turn it into a wild one. But it's not typically something, where it's space weather alone acting. It's space weather on top of something else that becomes a problem. And I think we're going to see that more and more. So, all right. Now, we don't get, you can't get transmission line information and all that kind of stuff and for anything other than the Western Hemisphere, sadly. But there are, at least if you're in Europe, there are other places that do this. Maybe not in a map form yet, but maybe that's coming. One of my favorite places is Helio Forecast. Excuse me, I'll tilt my thing because it's the daylight is getting worse, so I was getting a thing in the map. One of my favorite places, run by Chris Mostel, is Helio Forecast. Okay, you can see Helio Forecast space. Not only do these guys have a wonderful set of forecasting tools, but they also pay attention to transmission lines and lots of other data. So they are, to a great degree, a data repository. Let me go to I don't think I have, oh yeah. And they also have their space weather, like their version of Enlil. Let me say it's not Enlil, it's called Elvo, okay? Elvo. And I think that's how they pronounce it. And what's neat, and again, this is something I saw for many years in Chris Mostel's papers in scientific conferences, long before I saw it as an operational model. But I love this because Chris and his crew now, this space weather crew here in Austria, they're willing to make forecasts of what the solar wind is going to be, like real forecasts where you actually see it, and then they run this now bar so that it actually has accountability. So as the now bar populates, then the real data follows, and it's really kind of cool. Plus, you can see all of the CMEs that have been blasted out as these lines, and it allows them to do things and calculate things very, very quickly. So let me show you a live version of this. I believe I have it here. It's Hux T. Where's the other one? No. Where are you? Oh, poop. All right, let me pull it up again. I probably have it on that system, but let me see if I can do it here. Okay, so here again, that's the way it looks. And they've got lots of people that collaborate. And you can learn more about their team. This is a very new group of not group of people, but a new endeavor. I mean, they've really been ramping up over this last year or two to really put it together, and they've just done a fantastic time. So if you go under forecast, you can look at all the stuff. that they've got. So CME arrival time, I think that's where we get LVO. And you can see it here, and if you click on it, okay, so you can see the picture, right? But if you click on it, you get a movie. Oop, oop, right there. Come on, go away. There. Oh, sorry. But you can see all these CMEs, okay? And you can see how things, in this case, they're showing, I guess, data that's already hit, so you don't see the forecast. But as the model continues to move out, you'll see, I think they do a forecast. I think it's in this one, maybe it's not. But you can see, look at all the CMEs. So this is like the panel in NLOL, where you're looking down at the sun of the North Pole and then Earth being off to the right, okay? Notice in this one, Earth is not moving, just like it is, just like in SWPC. Earth does not move. You will see another version where Earth does move, but not with LVO, with something called Hux-T, which we'll talk about in a minute. Yeah, they don't have a forecast prediction here at the moment. But what's great about this model is that it runs quickly, and they run it for a very long time. As you can see, this one goes out to 11. They're probably already working on the next version. These become a bit more complicated because you can see, you know, a lot more data is available to you. And, oops, let me pop this back. Escape? How do I get out of this? Get me out of this. You could see lists of like LVO predicted arrivals, and you'll get something that's very akin to the NASA CCMC scoreboard page, so you can see all sorts of details on it. The only thing they don't do, unlike SWPC, is they don't predict like a KP or anything like that. But they do have error bars, which is nice. So errors in their measurements. You know, what's really critical is error in arrival time. Notice that some of them can be very large, right? And that's probably because it's a high angle or moving at a particular speed, or they didn't have very good observations to start with. But it's very, very nice because they actually care about getting it right. And they are not afraid to publish their, you know, their uncertainties. And now what's also nice, if I go back, on top of all sorts of stuff, right, you can have LASCO, you can get the CCMC scoreboard, you can see what's going on at Solar Orbiter. And on top of that, if you go to the dashboard, this is what's nice. So they have a nice little dashboard, just like SWPC has a dashboard, or it has multiple dashboards, but this one gives you all sorts of cool stuff, right? So magnetic field, where is this from? At L1, so whether it's Discover or ACE, they're using probably the active, whatever one's active. Then they're getting DST, so you have an idea of what DST is doing, very similar to KP, but more scientific and more low latitude. It's all about the ring current. Again, you can learn more about that in my E course series. And then you also get the Newell coupling, which gives you an idea of the power, the potential for aurora, okay? And this updates quite frequently. You can get also, you know, more information about a bunch of stuff. Pictures, okay, it's nice to have some of these pictures. Some of these are straight from Lockheed Martin, I think. You've got GOES X-ray flux, more pictures, movies of the latest going on at both SDO and the C3 field of view from SOHO. Here's LVO, so you could play that if you want. And then, oh, here we go, there it is. There's the prediction. I love this. They actually have a prediction of what the solar wind is going to do, based on recurrence, based on their models, whether the CME is coming or not. And they are not afraid to post what they think is going to happen. So it's really nice to see this because, like, for instance, they are showing that they don't think the high-speed wind is going to really be a big punch, right? So this likely is a CME, okay? But they do have, you know, this was, I think, an old CME. They're showing the recurrence, what they thought happened, or what did happen last, oh, wait, no. That isn't recurrence. Oh, it says recurrence model, NOAA. I thought they had an actual prediction. I'll have to look at that again. I thought that was not NOAA's recurrence. I thought that was their prediction. Huh. I have to go check to see whether or not they're actually making their own predictions with ELVO as well, or if they're just taking NOAA's model and then projecting their predictions from that. So my apologies. I'm not. I do need to check with Chris to find out exactly where the prediction is coming from. If it's just recurrence or if it's something else that they've done. But you can see errors on if they're looking at DST what their error bar might be. So it's kind of fun to have. Nobody really tries to do that. Here's stereo A beacon data, and I'll scroll down to here is not DST. This is Newell coupling, yeah. So again, potential for aurora. You can see they do slightly different with their data products, so that you can get more information. I think Aurorasaurus also does Newell coupling. You don't see that at SWPC, I don't think, anywhere in any of their data products. So if you're a real Aurora aficionado, this is a good place to get some of that stuff. And then, it's DST again. Hang on. Come on, where is it? Hold on. You can get lots of other stuff. I'm not going to go about it too much, even cloud forecasting and stuff like that, for their region especially. But here's what I wanted to show you, because we just finished talking about GICs, right, and what you might get in the Northern Hemisphere, right? They actually are trying to monitor GICs in Europe, over in Austria, okay? I find that fantastic. I don't know anyone else that's really doing that, other than going into the big, like ESA repositories. They might have a little bit here and there. But this is becoming a bigger deal, being able to actually look to see whether we're having disturbed current systems or maybe enhanced current systems. And you would probably see that with like lots of hash and stuff over the course of time. So for you folks who are, yeah, and that's the H, that's a perturbation of the magnetic field. But for you folks who are geomagnetically sensitive and are in Austria, this might be a good place to begin digging for data in your area, okay? So that's why I wanted to show Helio forecast. There's also another one, reason why, sorry, go to the top. I believe they have, I gotta find it. Solar cycle. Yeah. So if you go to solar cycle, remember how we were talking about Macintosh? Chris Mostel's group, they're one of the few. They will post the Macintosh predictions. So you wonder, how good is the Macintosh Lehman et al. Predictions compared to the average or the NOAA? It's blowing it out of the water, isn't it? There's an even more recent, more blown up version of you've got the mean solar cycle, right? So the kind of like the average solar cycle. You've got the Macintosh, you've got the NOAA prediction, and look how different. I mean, if they had just gone with the mean solar cycle of all 24 cycles prior to, they would have gotten a better forecast than if they had gone with their consensus. Crazy, huh? So our sun is still slowly but surely revealing its mysteries. And the Macintosh crew, notice the Macintosh crew do have a more extended declining phase, okay? And they have correctly predicted that solar cycle maximum is already over. If you were to believe the original prediction of the solar cycle from SWPC and their consensus, you would think we were just now hitting solar max. But we're past it, because we have coronal holes now. We have big coronal holes. That's declining phase. And no ifs, ands, or buts about it. The sun is telegraphing it's through solar max, both hemispheres. Okay. So these are wonderful reasons to like Helio forecast. It's like the only place you can get this publicly, okay, as far as I know. Now, Scott may correct me later, but I'll be sure to ask him. So Helio forecast, excellent place. There's the website goes into far more than you might, than just what I went over, but these are the main hits. Another one that's really useful, and then we'll pause, is the University of Reading. I always say it wrong. Forgive me. I'll say it both ways so that I'll always be wrong. But I think it's Reading, right? So here's the Hux-T forecast. We go to a live look. Come on. Hux-T is a great one. They update it quite frequently. And they've also got, as you'll see, expectation values, and they do ensemble stuff. So when you pull up this site, immediately you get to Hux-T. I mean, it's like, it's I think it's very easy to find it. Let me see if yeah, I think the website that I showed you, like if you go up to the space weather side, it immediately gives you this thing, because it's up here. It says Hux-T forecast. See that? So it's really easy to find. And when you play it, boom, look at all this. Very simple. Okay, again, you're looking down at the sun from the North Pole, with Earth being off to the right. However, this time Earth moves. Okay, so be aware of that. Earth is orbiting the sun. So it moves off of the Earth-Sun line. So if you're watching very intently here and not paying attention to where Earth is, you see a CME come across like this, and Earth is up over here. If you don't watch it actually cross this area, you're thinking this is the Earth-Sun line, and it's not. Okay? So in this case, the Earth-Sun line is not plotted. And that's a classic example where you saw that thing, that CME, come off of the sun, and you're thinking, oh, hey, this thing's going to hit Earth. And just because it just barely misses Earth. Okay, which is maybe what we're seeing right now. Is that let me pause this. I don't think so. Yeah, this was the other day. So too early. This is not the one we're seeing now. But this is the kind of idea, okay? Again, you can see the pinwheel, so you can see in this case this is velocity, this is speed of the solar wind. Okay, you get again the arrows here. But in this case, the numbers are, the origin is from the sun, so positive is going to be out toward. Okay, oh good, they all go positive. Good, I was thinking, they can't go negative, do they? So slow solar wind, right, is going to be on the purple side. Fast solar wind is going to be up at the yellow. Right, so in this case, they had this one just at the front edge of a fast solar wind stream. And as you can tell, there's no real, this is just a contour. I'm not even sure how they do the contour, but it's not like a magnetic flux rope or anything like that. This is not like, so you're going to see weird shapes and stuff like that. I'm sure it's probably just a particular kind of density contour that may or may not, you can see it stretch and break because it may not be, it's just in the ecliptic plane here. So that structure may be rotating and kind of rotating out of the ecliptic plane. So you're thinking it's just stretching, but you're only seeing a two-dimensional projection, like a shadow, right? I could do all sorts of funky little things and you'd think, oh, look, her hands are breaking off, her arms disappear because I go like this. And the shadow first has arms if I'm like this, but then, if I pull my arms in and the sun is behind me, it looks like I have no arms. Well, that's not what happened. I do still have arms. I just, it's just the projection onto that plane, onto the ground, is not a real good representation of what my shape actually is, because it's just a projection. It's just a shadow. That's what this is. These outlines are shadows. Okay, they're being cast, and so they can break up and look very odd. Just shadows. But it gives you an idea of where things are as it crosses, as they cross the ecliptic plane. Okay. Now, the other thing that's nice about Hux-T is that they give you some extra interesting information. Not only do they do ensembles, so they launch more than one CME. They'll launch a CME with the right with a certain type of attributes, but then they'll perturb those attributes a little bit, saying, well, maybe we got this off by a little bit, or we got this off by a little bit. Let's speed it up a little bit. Let's slow it down a little bit. Let's make it more dense. Let's make it a little bit more off on this angle. And so they launch a whole cluster of, like a family of CMEs, and they say, what does that do to the propagation? How long does it take to get Earth? And so they're able to build up kind of some idea with several different, I don't know how many they run, but they run some of them, as you can see, and then they also give an all sky map, kind of like the splash screen, if you look at NASA's NLOL, and they give you an idea of where that splash is at 1 AU. So what is if here is Earth and the sun is, directly behind it, you're looking at the sun from Earth's perspective straight into the plane of the page. If that CME comes in and hits that plane, the Earth, sun, the plane of the sky, what kind of splash would it make? How so if Earth is here, in this case, boy, Earth really dodges a bullet, because you got one that's hitting just below it, one that's hitting just to the east of it, one that's just southwest of it, and then one that's just northeast, say, but Earth is right here. So Earth is really not getting hit. It's getting sideswiped as these structures come through. So it gives you more information. And again, you get some level of uncertainties, which you can see down here. And it's a different it's a different model. It's a different set of eyes, different scientists that's taking the information and plugging it in. And so you're getting different results. And so it's kind of neat when you start grabbing all this. Okay, I'm going to grab this one from ESA. I'm going to grab this one from SWPC. I'm going to grab this one from Huxley from Reading, and I'm going to grab this one from Austria, from Helio Forecast. And I'm going to look at all these models and see what they say. Well, you can really build up a neat consensus potentially. And you can feel more comfortable if everybody agrees, or less comfortable if everybody doesn't. And then you can get a better feel for like the bracket, which is kind of what I do, right? I'll look at a whole bunch of models, especially when you've got a CME or a solar storm that's really hard to predict or what's going on. I will then take a look at all the different models and then try to intelligently put my own understanding in there, as well as looking at what they've done, and try to come up with something that gives us an envelope of what to expect, optimistically or pessimistically what to expect. Where do we assume that the event is eventually going to lie, So now you guys have access to a lot of the tools that I've been using. And hopefully more will continue to come on. And let's stop there. It's been a very long class thus far. Let me find out what you guys think. 2:09. So we've been doing it. We've been at it for 3 hours, folks, and I didn't even get to the data aggregation sites. Is this good? You guys, your head about to explode? Or is everything cool? I'm gonna put the chat back on. Let me see if I can put this here. And get the chat on. There we go. Everybody watching? Everybody sleeping? How's it going? See, every time I think I'm done, every time I think I've got I think I've got everything covered, and this will be the last class I need. It ends up always being, no, we didn't get through it all. So, reel in the tin hat comets. Oh boy. Was this, Jerry, tell me, was this because I was talking heliobiology? Did I throw a wrench in the monkey, so to speak, and everybody went off on the deep end? Right? Heliobiology is a wild, wild west subject, and sense of it is coming, guys. You just be patient with the scientific and the medical field. Just be patient with us all. We still have a ton of heliophysicists who don't believe that space weather affects anything medically. And that will change, but it's a slow paradigm shift that's got to happen. So don't put your tinfoil hat on, but just be patient. Be patient with us. Okay. Not much different than the SEN classes. What's that? Oh, Lisa. Oh, really? Okay. Oh, then the SWEN classes. Oh, cool. Yeah. Not much different. That's true. I mean, because I'm in advanced topics now. So, what you guys benefit in SWEN, I'm giving a little bit of a taste here, right? And I have to kind of walk that line a little bit because I don't want to either bore people or get things so far over their heads that they're not enjoying the class anymore. So, but thank you for that observation. So good. Miss Mitchell, mind blown. Okay. All right. Hopefully in a good way. Hopefully not like too much like drinking from a fire hose, although I know it is. That's what Lisa's probably talking about, is a bit like drinking from a fire hose. I know. There's just so much. There's just so much. And I'd love to teach it all to you. So just make sure, okay, and John Star says, very good. Just be sure to understand this course is supposed to be taken in bits and pieces. So don't feel like you have to ingest it all at once. Definitely come back and take a break and play with the data products and then come back and you can learn more. You definitely don't have to. You're diehards if you stay here the whole time. Heads are exploding. Okay. Jesse says, I would love to learn about the Newell coupling in future courses. Okay. I will keep that in mind. Got it. Okay. Wide awake here. Good, Nick. I'm so glad. I'm cool with my thin foil hat. There we go. The thin foil. It's not a tin foil hat. It's a thin foil hat. Got it. You just line the inside of your baseball cap so no one can tell, right? There you go. Yeah, Dave. Yeah, definitely go back to the beginning. Don't watch from this point because you'll be like, what are they talking about? I can't understand it. Can you tell me why I'm going very sleepy if flux is under A? What do you mean A? You mean talking about X-ray flux? When you get to the A level, you're looking at the instrument noise, so it's not going to be space weather that's going to affect you then at that point. Maybe, but I'm still here. Thanks, Jeff. I appreciate the honesty. So at least I haven't scared you away. Even if you're taking a snooze, I completely understand. Old school nuts. There we go. Let's see. I'm getting hit hard by all this. I feel like I'm going crazy and on the verge of a heart attack. Oh, don't say that, Darcy. Take your time. This stuff is not always easy to absorb. Okay, so don't worry about it. And if you don't have the background, right, with some of the other mini courses, you can. I actually have on my website like a synopsis of how you take the courses so that you can learn at your own pace. But because this is an advanced topic, it can be a bit intense. And so at some point, I think I probably will need to go back and teach some basics again, because I think some of the old basics I have, I wasn't even on green screen yet. I was still on a television screen. So I can probably redo some of those again, but it's going to be up to the Patreon folks how I do it. I already got a thing about Newell coupling, so that's very cool. I could definitely get into more of the Aurora stuff. I don't want to step on a lot of Aurora photographers' toes, though. There's a lot of people out there that do a lot of stuff focused on photography and Aurora. I don't need to redo that stuff because that's their bailiwick. And like Vince Ledvina, for example, has some really good talks about that kind of thing, as well as do others. Liz McDonald as well. And Mary Beth Kaczynski, she's starting to do stuff like that as well. You've seen several of these people, both Vince and Mary Beth, in my forecasts from time to time. So Andy, you say been great, good. Okay, and Sven, I see your tinfoil. The paradigm shift will come with help from star families. Okay, I'm sorry, things are scrolling so fast. I see that vivid magic. Yeah, I'm glad you did too. This is totally real effect with CMEs, and this is not for the faint of heart. Agreed, Darcy. Yeah, and it is real. But again, space weather acts in tandem with other things that can make it really difficult to understand. It's good. I like the refresher. The data products are always awesome to go over. Good. Thanks, Lisa. I appreciate that. Be as technical as needed. Okay, will do. I mean, again, this is for the patrons, and Nick, you're all part of that family. So, the level of complexity really comes from what my patrons are, what the mini course tier says to do. And so I will do that. But any questions? I'm not saying, thank you for the ROTI movie. Oh, good. Marco, I'm glad you like it. I'm working on it, man. I'm working on it. Tell me if you think, do you like the ROTI, that ROTI better than DLR's ROTI? Do you like my geochron map and the way that works? Or do you like the way that DLR does their little 2x2 grid squares? I'm still kind of on the fence about that. So let me know. I think I had one Friday morning. You guys, you poor guys. I see we got some heliobiology folks in here, you sensitive folks. I'm so sorry. Yeah, it's kind of a pain to have to deal with that on top of everything else, right? I mean, goodness. Okay, but that's part of how the heliobiology group in my Patreon crew, how we've all kind of learned, right? I learn what they're sensitive to, and I try to figure out data products that help. And some of them have, like Noy, for example, has told me about, hey, I use this data product for this. And I'm like, really? Wow, what a great idea. So I've learned as much from them as they have from me. Okay, are there going to be more cosmic rays? Wait. Yeah, are there going to be more cosmic rays since there is KP0? No. The sun is still, it's magnetic. We're talking about the heliosphere. So the solar wind and everything is still very, very strong, and there's a lot of dynamic pressure and a lot of strong magnetic field out at the termination shock. So that's not going to happen until we really begin to crater toward solar min. Just because we don't have any geomagnetic storms doesn't mean that cosmic rays are going to start really impinging on us again like they do at solar minimum. The cosmic ray flux is right now much, much lower than it is at solar minimum. So even when we get a Forbush decrease, that's just another, deepening of that compared to where we typically are. But during solar minimum, that's when that cosmic ray flux is going to rise back up again. The issue that we're hopefully getting away from is that as our sun wakes up, granted we're going to have more G5 storms, so we're going to have to get used to this. But the nice thing is that we'll never get the intense cosmic ray fluxes like we've been getting the last two solar minimums. The last two solar minimums were horrible. I mean, people who were flying, and as I've said this many times, people who were flying parts, for cell phones and stuff, they would fly them over the poles, and the parts would be great when the plane took off. They'd fly this 10-hour flight over the poles to get from Japan to America, let's say, and by the time the parts landed, they would test the parts, they'd all be dead. Why? Because they got irradiated so badly over the poles that, when as I talked about how the cosmic rays has unimpinged, unimpeded precipitation into the polar regions. And so things were getting so irradiated that they were breaking. But luckily, because we're coming out of that solar minimum, the deep solar minimum, and our sun is waking up again, our solar minimums will no longer be that deep. So the cosmic ray fluxes won't be quite so high, and that's a positive thing. Okay, so that's the thing with space weather. There's no such thing as a safe day, because if you're at solar maximum, then you're dealing with all the sun's activity stuff and the space weather from that. But when you're at solar minimum, maybe our sun isn't acting up, but then cosmic rays are a pain in the butt. So there's always space weather from somewhere, right? Irrespective of what part of the solar cycle you're in. Okay. So aurora for me is scatter mode time. That's pretty funny. Certainly it's important to get the visible light from the sun. As human X-ray absorption might be important too. No, X-ray absorption doesn't happen on the ground. Our atmosphere takes care of that. All that super high energy stuff, that's all absorbed by the upper atmosphere. So this is why you can't see EUV images except with space telescopes. You can't see it from the ground. You can't see the corona from the ground. People go, oh, it's CGI. No, it isn't. It's actually that the upper atmosphere absorbs all that stuff up to UV, right? We get UV. Why don't we ever have sunscreen for gamma rays? Well, it's not because gamma rays don't exist. It's because our upper atmosphere is the sunscreen, okay? We don't realize it, but we have what we call atmospheric windows, and it prevents certain light of certain energies reaching us. And we have these atmospheric windows, thank goodness, because that protects us. It also is why our skin is a yellowish brown as opposed to green. If we were in space, if you were to look at the sun in space, you would see a greenish yellow sun, not a yellow sun. Why? Our atmosphere scatters the blue light, takes out the green, takes out the blue light, so that makes the green disappear, and what we're left with is yellow. And our skin, right? I don't care if you're a completely white, pinkish person or you're a completely chocolate person. We're all just shades of yellow. Okay, we're all shades of our star. Our star has colored our skin. Okay, and you blend it with the red of our blood, and you get all the shades of peach and pink and purple, or not purple, peach and pink and tan and brown and chocolate, and all of those shades. It's all based on the light spectrum of our star blended with the sky of our planet, creating who we are. Right? We are unique in all the universe. It's only this planet and this star that creates beings like us. It's cool. I think it's cool. Anyway, I'll get off that little soapbox for a sec. Questions? Anybody have questions? Everybody's saying it was fab. I'm so happy. Thank you so much, guys. Dr. Tamitha, wishes and blessings. Oh, thank you. And be true to your path. That's sweet. Thanks, John. Much. Your ears are screaming. Yeah, well, I'm not sure it's a space weather unless we have a big solar flare right now, right? Okay, let's see. Well, dang, if you think the CME effects are bad now, just wait 5 years. Well, we'll see. I mean, we're going to have a couple big CMEs at the last gasps, guaranteed. But right now, what we're gearing up for is the fast wind from coronal holes. We'll get anywhere from G1 to G3 level storms if there happens to be a stealth CME hidden in there somewhere. And we'll get it every 14 to 20 to 28 days, 27 days. And that we're entering the era in which aurora photographers love, because they can predict when aurora is going to happen with a 27-day cadence, and foresight, and be very, very accurate. And satellite operators hate it, absolutely hate it, because the Earth's radiation belts really get zinged up, and you get lots of anomalies for spacecraft. And it'll be interesting. It'll be very interesting to watch how Starlink behaves over this declining phase of the solar cycle, because granted, we're not getting necessarily the big G5s all the time, but we're getting G1, G2, G3 every 14 to 27 days. And so the atmosphere goes, right before too long, it just keeps getting pumped up. Every zing is going to pump it up and heat it. And it'll be very interesting to see whether that has an impact on these LEO satellites or not, especially these little teeny tiny ones with these big drag parachutes. They're what I call their solar array, which I call the big drag parachute. We've never had these kind of beasts in constellation style like we have now in these orbits. So we'll see. We'll see. It'll be an interesting time. Even I'm not sure how it's going to happen. Okay, any questions? Let's see. Someone asked, Dave, you were asking what modes. I'm not sure what modes. What do you mean? Maybe I'm missing something. Isn't the sun white when viewed from space? Yeah, Neil deGrasse Tyson likes to think that. Sure, it's white when viewed from space with our eyes, because our cones get saturated. If your red, yellow, and green, or red, green, and blue cones are saturated beyond the point of belief, it's going to be white. But if you actually were to look at a spectrum of the actual light coming from our star, it peaks in the green-yellow. Yeah, it's kind of a greenish yellow. So the peak of the light flux, electromagnetic flux from our star, is green-yellow. Yeah. So the white is an artifact from our eyes not being able to handle the saturation. Okay, it's not the actual color of our star. And if Neil were a little bit more precise, he'd know that. But don't get me started on Neil. Right? He thinks space weather is just weather on other planets. So basically reduces the entire field of heliophysics into nothingness with one statement in Star Talk. Yes, Carl Sagan, much better. What do I think about the movie Contact? I loved it. I read the book too, but I'm a Sagan fan, right? So the only thing I think Sagan did wrong is to poo-poo astrology and those who believe in that stuff, because that has a place in, it's one of the oldest ways of looking at our stars, and I think it has just as much a place in our human evolution and the way we look at the universe as science does, as the physical sciences do. And I think he poo-pooed. I think he ripped too hard on astrology, to be honest. I think it doesn't matter why you look at the stars and why you look up at the sky. It's the connection that's important. So that was my only kind of pullback with Carl. But outside of that, I loved him. And Jack Horkheimer, too, in case you might know who he is. What are those dark, shadowy regions popping out on both sides of the sun visible on LASCO C3? Okay, if you're looking at LASCO C3, you are not going to be looking at anything on the sun because LASCO is a coronagraph. So you're looking out only at the solar corona and out into the beginning of the solar wind. So shadowy regions could simply be, one is probably the pylon that's holding the Coulter disk. Other may just be less dense areas of the solar wind, so where they're not streamers. Because what you're looking at is scattered electron density. So where the scattered electron density, where the density is low, the electron density is low, you're not going to get scattered light. So it's white light scattered literally into the detector. And so you're not going to see that. So if there's shadowy regions, then it's likely because there's just no real electron density, which means it's probably not a streamer. Now, if you're talking on the disk itself, then you're probably talking about coronal holes, okay? But I need to know if you're actually talking about coronagraphs or not. And if it's something else that's transient, it's probably an artifact. You know, SOHO's been up there for so long. There's all sorts of artifacts that occur. Oh, gosh. Don't even get me started. The poor thing. That thing's old. That spacecraft is older than probably some of the people watching this stream. It's been a real workhorse for us for so many years. Okay, does the sun activity cause low-level humming noticeable to people? Humming like in your ears humming? The sun wouldn't cause that, no. So, you know, that's something that you might need to probe some other way. If you're seeing a correlation with solar cycle activity or solar activity, first of all, find out what phenomena that you think you're correlating with, because then that leads down the path of what could be the issue. Is it geomagnetic storms, so it's geomagnetically related? Is it radio burst? So if it's solar flare, it could be radio burst related. I do know that whales and other migratory animals have a real problem with radio bursts. It disorients them, okay, because these are really broadband screams by the sun, and that upsets some chemical something in their brains. Don't know why, don't know how. There's a couple papers on it though you can read, and the biologists who study this stuff understand it far better. But it upsets something there, and that's what they're finding, is that it wasn't. They always thought it was the geomagnetic storms that did this and cut their magnetic compass off, but that's more for birds. The ones that the migratory animals that are mammals, for them it seems to be radio bursts. Isn't that wild? So that's what I mean by with space weather, you really have to look at the phenomena, and you can't conflate the different phenomena together because it'll mislead you. And then typically, you know, that depending upon what things are correlated with or what they're not correlated with, really more of what they're not correlated with, can help eliminate different hypotheses. Okay, but that's something that you should do with a doctor, obviously, if you can. And if you have a heliophysicist who can help you along, then that's great. But you know, this field is very slow to move forward. Heliobiology is very slow to move forward, and trying to find a heliophysicist who will actually give you the time of day when it comes to medical stuff is still hard. It's not impossible, but it's hard. So, is that why the green pops up at sunset? No. If you're in our upper atmosphere, or if you're sitting in Earth and we have an atmosphere, it's going to be because of the atmosphere. If you see that green flash, it's not that. That's an atmospheric phenomenon. If you were at Mars, right, during the day the sky is red. During sunset, the sky is blue. It has everything to do with the planet of origin. Okay, that's what I mean. If we had been born and raised on Mars, our skin color would be different. Isn't that crazy? We would literally be different creatures that had evolved if we had evolved on Mars, because it's not just the sun that dictates your skin tone. It's also the planet. It's the atmosphere of your own planet. It's so cool. Ah, Mom and Dad. I'm just kidding. Anyway, I just find that so tickling. It just tickles me. All right. Yeah, Minnie too. Thanks for the reply on Carl. Oh, you're welcome, Alexander. Absolutely. Astrology is a fantastic way to timestamp events in your life based on the cosmos. I think it's fantastic. I love it that it's a clock, right? The cosmic clock is, the stars are like cogs in a massive clock. We're like inside a massive grandfather clock, and we get to watch all the cogs spin and tick and stuff. It's just the ideas of like all the little tidal poles on everything. You know, we're all connected. We're all connected that way. So I find astrology fascinating, even though I don't follow it. You know, I'm not an astrologer who goes off and does all sorts of stuff. I still find the art fascinating, and I will call it an art because there is a bit of art in it, right? It's got some science, but it's got a lot of art. It's hard to, it's a squishy arena, but it's a neat arena. Right, the interpretation of astrology is where it gets more controversial. Right. I mean, it can still help or benefit people. And I don't care what brings the love of the stars to you, be it science, be it art. Let whatever it be. Right, so that's my take on it. Soho is younger than me. Yeah, me too. But you know, not by a hell of a lot. But it's a lot older than a lot of people, right? There's several generations now that Soho is older than, right? It was launched in what was it launched? Was it launched in 95 or 91? I always forget. I think Yoko was launched in 91 and Soho was in 95. Someone correct me on that. I have too many things in my life. I've been in my coding cave for like a week straight, trying to get those data products, and so I'm having a hard time like not speaking math, not speaking numerical recipes in Python. It's tough right now. It's like English, Tam, English, and trying to access old memories is not working very well. Okay. Where were the readings last year? Much of what we noticed and wrote down, the storms had to kill the networks. Oh, you guys are, sounds like you're having a fun conversation. Cool, right on. Is a geomagnetic storm possible this year that could significantly accelerate volcanic eruptions? You know, what Hadimon? Gosh, that's a Nobel Prize question. You know, the problem that we have is not so much that is there a potential mechanism by which these things could be affected by space weather. The $50,000 question or $50 million question is how much, right? We can see mechanisms by which these things can exert forces. The problem is how big are those forces? Number one, over what area are they acting? Number two, because you can have a tiny little force that acts over a large area, then it integrates into something strong. And how much does a volcano or an earthquake, you know, a fault line or something like that, how much does it need, right? How much force does it need? And we can't answer those main questions without the geophysics, you know, the geophysical folks answering the questions about how earthquakes are generated, whether they can predict them, you know, just by the primary drivers of these processes. Geophysics is not advanced enough as a science to be able to quantitatively predict or quantify a lot of these parameters. And so therefore, it doesn't matter what answers we come up with in space weather, we've got nothing to compare them to. So we can say, yeah, there's a mechanism by which, but then you say, okay, does it actually affect? And we go, I don't know, because we don't know how much is needed. And those questions, sadly, at least from a mainstream science point of view, are going to be left unanswered, possibly for decades, until we can get the geophysics folks to get their questions answered better in a more rigorous manner. And it's sad because volcanoes and earthquakes are super important, right? But because they both happen so frequently, they correlate with everything. And so just because you have an earthquake and a volcano that erupts or, you know, shakes at the same time that there's a space weather event, that doesn't mean anything, sadly. I could sneeze. I've said this many times. You sneeze, I could find an earthquake that correlates with my sneeze. What does that mean? Oh, maybe I'm powerful, more powerful than I thought I was. No, it just simply means that earthquakes and volcanoes occur all the time. Even small little bubble ups, right? I mean, what do you consider an earthquake? What do you consider a volcanic, volcanic activity? It's always active. There's always some fault line somewhere on the ring of fire, let's say, that is always throwing off stuff. And if all you need is the window of a day, which I've even seen people pull out a window of a week, saying, oh, there's a coronal hole entering the Earth's, that means going to be an earthquake this week. And sure enough, there's an earthquake. As a matter of fact, there's like 1,000 earthquakes this week. Oh, but there's one that's a 7.0. That was definitely due to that coronal hole. What? Are you kidding? It doesn't. So it's great to speculate on that stuff, and I really applaud the fringe scientists who continue to keep that going, because the more they keep it going, the more it whispers in the ears of the mainstream folk that, at some point we need to look at this. At some point we need to try to find a way of quantifying this and get funding to do this work. But right now it's too much of a speculative arena that even if a mainstream scientist wanted to chase that kind of work, they're not going to get paid for it. So mainstream scientists get paid to do science, right? And if they can't get funding, they don't have a job. So they'll do something else. So a lot of people say, oh, well, mainstream scientists don't want to do it because, they're big brother and the government tells them don't do it. It's like, no, it's literally because they can't get funding. They don't do it because they need to get paid and they need to feed their families. So they'll go to where the low-hanging fruit is to be able to get funding, right? And they'll keep that idea in the back of their head that I'd really love to chase this. And maybe in their own time they may dawdle a little bit and play around with it and perhaps come up with a hypothesis, and then maybe even write a proposal to try to get funding. Likely get shot down because it's going to be reviewed by a set of peers who are going to say, oh, come on, there's no connection. Or maybe there's a connection, but this isn't a robust enough study that we can fund, that we know that you're going to have any real results that anybody can lean on and use. So we're going to shoot this down. So that's the problem with mainstream science. So that's why I always say, fringe science, mainstream science and fringe science are like the right hand and the left hand, right? They need to be always shaking hands. They always need to be together. And mainstream science keeps fringe science grounded, but fringe science gives mainstream science wings. And I will always keep that philosophy. Okay, hopefully that answers that. All right, guys, any questions specifically on the data products or anything like that? Yeah, I know, the Ring of Fire, Johnny Cash, I know, I hear it too. I can't sing like Johnny Cash, otherwise my voice is too high. Solar flux, I don't know for running away, that I don't know what that means, like what we were asking specifically. Okay. This is interesting. Has anyone started monitoring or recording how the Earth's climate is affected relative to its position to the sun, relative to its position in the cosmos? Yeah, a lot of people have done that. The problem is, when you start doing that, the time scales over which things happen are so slow that very rapidly you run out of data, good quality data, right? I mean, think of the time scale of a human being. Really short. Think of the time scale it takes for us to move to any significant degree, our heliosphere to move to any significant degree in a different place in the cosmos. Millennia. Do you think we have decent data products that we could stitch together over a timeline that spans hundreds, if not thousands, of generations of human beings? We've only had a modern age for a very short time. We've only had 25 solar cycles that we can count quantitatively. That's why we're in solar cycle 25. That's when we first started counting them. We started counting sunspots. Prior to that, we have proxies, ice cores, notes of people who lived prior to us. The I Ching, for goodness sake, in 28 BC talks about sunspots in the sun. But we don't have really good measurements. So that's where the problem lies. It's like, once again, people say, oh, you don't chase it because you don't believe it, or you don't chase it because you're trying to hide it. No, we don't chase it because we don't have robust enough data sets to go chase that kind of thing. Right? We need quantitative analyses. And in certain areas, we can speculate and think about those things, but we can't physically go and do robust science in those arenas, simply because we just don't have enough data. When the time scales of these cosmological phenomena are unbelievably long, right? Even solar cycles. I'm frustrated that I've only lived a few solar cycles, right? I mean, that's hardly enough statistics to understand how the sun works. And we're going to have to leave it. I know I'm going to die, and we're not going to have much more progress than we have now. A little bit more, but not a lot. Why? Because we don't have that many. Some more solar cycles are going to happen before I pass on. We have to leave that work to the next generations, right? And then 200 years from now, they're going to be working on whatever project they're working on, and they're going to scream that back in the 2020s, we didn't have a certain data product because we hadn't thought of it yet, or we hadn't developed the instrumentation to handle and do that type of data product, that kind of data analysis yet. We didn't have the right satellites or whatever it is, right? We didn't have AI, I mean, there's an infinite number of ways that we can see how the past fails us in terms of its lack of technology and lack of measurements, and how by shifting that forward, how much we're going to fail the future. Because right now we don't have the types of techniques and data products and analyses and observations that they will have in the future, that they'll need to be able to do the analyses that they want to do at that time. It just is. It just is. Okay. All right, guys, hopefully that helps answer some. It sounds like you guys got a really good feel for the data products, because we're getting kind of like a lot of off-topic questions, be able to be a little bit philosophical here at the end. Does the sun have radiation belts? No, it does not, because it's constantly blowing its solar wind out. Earth has radiation belts because it's not blowing a wind, so it's not blowing particles out of itself. The sun, its atmosphere is literally exploding out of its surface. Its atmosphere is reaching escape velocity and leaving all the time. So it can't have stable radiation belts. You can have neutral dust, right? They do talk about dust rings really close to Earth. Those neutral dust particles, there's how they stay in place, and the reason for that is because they don't see electric and magnetic fields, so they have a much better chance of staying in place if they don't hit any solar wind particle, because there's always stuff being blown out. But the neutral particles have a much better chance of staying in place than ions and electrons, because ions and electrons see that solar wind that's blowing out at all times. Hopefully that helps to answer that. I know that's not as clear as you might like, but we're getting to the end, and Jerry's telling me it's time. I see you, Jerry. I see you. Okay, let's see. A couple more questions, and then I'll go. Do the NOAA Geospace Magnetosphere movies have any practical usage? What do you mean by practical? Substorm prediction, satellite operators. Wow, Marco, that's a really good, I don't know where you are. That was a really good question. I think you're right here. Yeah, that's an excellent question. And I don't know of any satellite operators that use those magnetospheric models, because models are models. They can give an oversight, but they're very limited, and a lot of them are, probably they're more for magnetopause, and possibly a look for how far things go down the tail, maybe the shape of things, but yeah, it's still very academic at this point. Yes, you have them in operations. How well they're being used, I don't know, but my guess from the operators that I know, they're really not. They're more for show. So, and for the potential of, hey, here's what could be used. Hey, here is an idea. If somebody wants something like this, at least put that out there as a baby step for where we could go from here, you know? So I think that's more of what it is, okay? Hopefully that answers that. Okay, you're welcome, William, for the updates. Is the Oort cloud kind of like radiation belt? I don't know. The Oort cloud is, I mean, it's not in, and because I'm not an astrophysicist, I don't know what the exact magnetic field configuration is. Radiation belts are trapped. I don't know if the Oort cloud is trapped in the same way that, you know, it's more trapped in a spiral arm or something. I don't know. I don't see a governing body that the Oort cloud is trapped around. But then again, I'm not an astrophysicist who studies that. But the same kind of rules apply. So if there is a body that has some type of magnetic field, then you can't have trapped drift paths. And but I don't see that being the case in the Oort cloud. I just not that's my perfunctory reaction, but I could be very wrong. Again, that's outside of my field of expertise. I stay inside our termination shock. So things inside the termination shock, inside our own heliosphere. That's why I'm called a heliophysicist, right? That's my bailiwick. And outside of that, I'll tiptoe out there because a lot of the physical processes can be the same, but I'm not nearly as well versed. So I got to be careful. Okay, guys. Let's see. Any other last questions? I see. Thank you, Spirit. I appreciate your comments. You're very welcome, Nick, for the lecture. Okay, guys. Some sweet comments there. You're very welcome, guys. Okay, let's see. Have I seen any modules and data sets being processed that you're excited to come to fruition? Mine. Geocron. The last one I was super excited about was the WAM IPE model, and that's one of the ones I'm going to be mining here soon. That SWPC put out. Since then, not yet, but I haven't looked super deeply. I will be more excited when I see bigger data sets come out with GPS, using GNSS and GPS data for things like scintillation and now casting of the ionosphere. When that starts becoming a thing, that may be coming from MIT Haystack. We'll see. We'll see. We'll see what we can get them to do. Phil Erickson may go, what? No way. Come on. We're not doing that. We'll see. All right, guys. Those were intense data products. Love. Oh, good. Awesome. I'm glad you guys liked it. Yeah. Go check out some of these sites, like I said, and we'll go into more of that in the data aggregation sites next time. So there will be a part 4. We'll get into more in depth. I'll talk about SolarHam. I'll talk about NASA's ISWA, as well as, you know, here's a picture of ISWA from NASA. We'll talk, that's the old version of it. We'll talk about ESA. Oh my gosh, is this a deep data set? There's more of it there. And we'll talk a little bit about the Australian government, their Bureau of Meteorology. They've got one for people down under. I'll try to be good to you guys. Of course, Space Weather Live, right? There's several Space Weather Lives. There's G7IZU for ham radio, and neutron monitors even, and then SolarHam. Some of you guys are amateur radio operators like SolarHam as well. So those will be some of the things that we'll go over next time, okay? So enjoy. I'll try to put this back on a black screen so I can keep this thing up. Here we go. Okay. So thanks for everything, guys. I hope you enjoyed this. And yeah, we'll have a part 4. And Patreon members, let me know in the comments and stuff. Oh, let me check the comments real fast. Let me know what you think of the Geocron data products. Let me check real fast before I quit the stream. I know, Jerry, you're dying to get out of here. Let me check to see, however, if there are questions in Patreon. Oh, Lynn Bennett, you haven't been able to access the live chat. Well, Lynn, be sure to ping me. I'll see if I can help you figure that out or whatever. So, because that shouldn't be the case. You should be allowed to get in here because you're not in here, right, Lynn? Has anyone seen Lynn Bennett in here? in the chat? If she is, wave hands or something like that. Otherwise, Lynn, I will ping you on Patreon and see if we can figure out what the issue is and how to get around it. Okay, I don't want to leave you out for something that should be easily fixable. Okay. All right, guys, thanks so much for everything, and enjoy, and go play with these data products, right? That's what they're here for. Okay, guys, bye. Thanks, Jerry, I see that.